Something fell into a black hole today. Not a comet, not a star. A question. Physicists have spent a century building equations precise enough to predict the orbit of a planet to within meters, to track the age of the universe to within a few 100 million years, to describe the behavior of particles smaller than anything that has a name. And then a black hole opens up, and those same equations, the ones that have never failed in any laboratory, on any scale, across any experiment we've ever run, produce the word infinite. Not large, not extreme, infinite. In physics, that word is not a result. It's a confession. It means the theory has reached the edge of its own ability to speak. Something real is happening at the center of a black hole matter, compressing past every pressure a neutron star can generate, past every density our instruments have ever measured, and the best framework humanity has built to describe gravity simply stops working at that point and hands the problem to someone else. 4 separate groups of physicists looked at that same confession, that same infinite, and came back with 4 completely different answers about what actually exists on the other side. Not 4 variations of the same idea. 4 answers that contradict each other at the most fundamental level about whether space continues past the horizon, whether information survives, whether the singularity exists at all, and whether the inside of a black hole connects to somewhere else entirely. All 4 are mathematically serious. None of them can currently be tested. And that combination rigorous math, zero confirmation, is exactly where physics gets interesting. Picture yourself drifting in empty space, somewhere near the center of our galaxy. Nothing around you seems unusual. No wall, no warning signal, no change in the light. You are falling freely, which, in general relativity, means you feel no force at all, the same weightlessness an astronaut feels in orbit. Your body doesn't register anything strange. And then you cross a line that has no surface. That line is the event horizon. Not a physical boundary, a mathematical one. The precise distance from the center at which the geometry of spacetime has tilted so steeply inward that every path forward, in every direction you could possibly move, now points deeper. Not toward the center the way a ball rolls downhill. Toward the center, the way time points toward tomorrow. Not a force pulling you, but the structure of what forward means having permanently changed. This is what general relativity actually says happens inside a black hole. Escape isn't merely difficult. It's geometrically forbidden. Even light moving at the only speed the universe allows as a maximum cannot find a path that leads outward. Because outward, past that threshold, is no longer a direction that exists. Now, here is the part that took me a while to fully absorb. The experience of crossing the event horizon depends almost entirely on the size of the black hole. For a stellar mass black hole roughly 10 times the mass of the Sun, compressed into a sphere about 30 kilometers across, smaller than a mid-sized city, the tidal forces near the horizon are lethal long before you reach it. Gravity pulls harder on whatever is closer to the center. Across the length of a human body, that difference in pull, a few decimeters, at most, would be enough to stretch you lengthwise and compress you sideways until the atoms that made you no longer hold their structure. The process has a name in physics, spaghettification, which sounds almost comic until you think about what it actually describes. But for a supermassive black hole, the kind anchoring the center of a galaxy, 4 million solar masses or more, the horizon is so vast that the tidal gradient across a human body near it is gentle. You could cross it intact, conscious, still thinking, with no local indication that anything irreversible had just happened to your future. The fatal compression would only come later, deeper in, as you approach the center. That asymmetry, larger black hole, gentler edge is one of those facts that physics produces without apology and leaves you to sit with. What happens to time during all of this is stranger still. From your perspective, falling freely, your clock ticks normally. Nothing feels slow. But to someone watching you from far away, say, hovering at a safe distance, your image would appear to stretch and redden as you approach the horizon, your motion slowing, your light pulling toward longer wavelengths as it climbed out of deepening gravity. Eventually, you would appear to freeze. Not because you stopped, but because the light carrying each successive moment of your fall takes longer and longer to reach the outside. You would seem to hang there, fading, a permanent image at the edge. Two different realities, same event, both accurate. General relativity doesn't resolve that contradiction. It simply contains both descriptions simultaneously and treats them as equally valid depending on where you're standing in space-time. And then you reach the center. Or rather, the equations reach the center and stop being able to say anything meaningful. General relativity predicts a singularity, a point of infinite density, zero volume, curvature that the math cannot define. That word, infinite, is not a description of something extremely large. It is the same flag that appeared in the opening, the theory running past the edge of its own language. Something is physically happening at the center of a black hole. The math just cannot follow it there. Which is the first place where the four competing answers about what's on the other side actually begin to diverge. Because if the singularity isn't real, if it's a failure of the theory rather than a feature of nature, then something else exists at the center. Something the equations of general relativity alone cannot see. And what that something is depends entirely on which branch of physics you trust to fill the gap. Gravity doesn't pull everything equally. This is not a detail. It is the entire mechanism behind one of the most extreme processes in the known universe. Every object with physical size occupies more than a single point in space, which means one side of it is always slightly closer to a gravitational source than the other. And the side that is closer gets pulled harder. The difference is usually so small, it disappears into the noise of everything else. The moon pulls your feet toward it about 1 part in 30 million more strongly than it pulls your head. You will never feel that. But the oceans do accumulate it across a planet with a radius of roughly 6,400 kilometers. That same fractional difference is enough to raise the sea surface by about 1.5 meters on the side facing the moon and produce a corresponding bulge on the far side. What you experience as a high tide at the beach is gravity doing slightly different things to points separated by a few thousand kilometers. Now take that same logic and compress it. A stellar mass black hole 10 times the mass of the Sun collapsed into a sphere roughly 30 kilometers across, about the distance from one side of a mid-sized city to the other, produces a gravitational gradient near its event horizon that is not 1 part in 30 million. Across a single meter, The difference in gravitational pull can exceed 1 billion times the gravity you feel standing on the surface of Earth right now. Across the length of a human body, call it 1.7 meters, that gradient accelerates your feet and your head along paths that diverge faster than any nerve signal can travel between them. There is no sensation of stretching, no moment where you register what is happening. Your body simply stops being a coherent object before any part of it can report to any other part. Physicists call this spaghettification, which is, given what it describes, an almost affectionately absurd word. What is actually happening beneath that name is a direct consequence of how general relativity understands gravity not as a force transmitted through space, but as the curvature of space-time itself caused by mass. Objects don't get pulled toward massive things. They follow the straightest paths available through a geometry that has been bent. Near a black hole, that geometry changes so steeply from one point to the next that the straightest path available to your feet and the straightest path available to your head are genuinely different trajectories. They diverge. The space between those 2 points is being stretched not as a figure of speech, but as a literal geometric fact. Your body, occupying both points simultaneously, is stretched with it. We have watched this happen. Not to a human body, but to stars, which are considerably larger and therefore subject to tidal gradients across distances of hundreds of thousands of kilometers rather than 1.7 meters. When a star drifts within what astronomers call the tidal radius of a supermassive black hole, the distance at which the black hole's tidal gradient exceeds the star's own self-gravity, the process begins. The near side of the star accelerates faster than the far side. The star elongates along the line connecting it to the black hole and compresses perpendicular to it. The star's own gravity, which had held it together across millions of years of nuclear burning, loses to the geometry pulling it apart. It tears. The debris gas that was, seconds earlier, part of a coherent stellar interior forms a thin, bright stream that spirals inward toward the black hole, heating to temperatures of tens of millions of degrees as it compresses and collides with itself. The radiation released briefly outshines the entire galaxy hosting the black hole. A single star, destroyed, visible from hundreds of millions of light years away. There is something worth pausing on here. The same tidal gradient that would destroy a human body in milliseconds near a stellar mass black hole becomes, near a supermassive one, almost gentle at the horizon. A supermassive black hole, millions or billions of solar masses, has an event horizon so vast that the change in gravitational pull across a human body at that boundary is survivable. If the black hole anchoring the center of our galaxy has a mass of roughly 4 million suns, its event horizon spans about 24 million kilometers a distance. You could fit nearly 17 suns across. At that radius, the tidal gradient across 1.7 meters is negligible. You could cross the event horizon intact, conscious, with no local physical sensation to tell you that the geometry you just passed through has made your return to the outside universe permanently impossible. The fatal stretching only begins deeper inside as you fall further and the curvature steepens. It comes gradually, at first a slight unevenness in how different parts of your body accelerate. Then faster still, as the gradient that was spread across 24 million kilometers at the horizon compresses into smaller and smaller distances the closer you get to the center. Eventually it reaches the scale of molecules, then atoms, then the subatomic particles within them. Protons are not infinitely rigid. At sufficient tidal acceleration, The strong nuclear force holding a nucleus together, the force that requires temperatures of 10 million degrees just to initiate fusion, loses to the geometry pulling it apart. What matter becomes past that threshold is not something any current framework can describe with confidence. Because that is where general relativity stops speaking clearly. The equations predict a singularity at the center, a point of infinite density, zero volume, curvature that the mathematics cannot define. And as established earlier, that word infinite is not a description of something extremely large. It is the theory reaching the boundary of its own language. General relativity was built to describe spacetime at scales where quantum effects are negligible: planets, stars, galaxies, the large-scale structure of the universe. At the center of a black hole, those quantum effects are not negligible. They dominate. And general relativity alone has nothing to say about what happens when they do. What we can say is this: the tidal gradient that begins as a gentle unevenness you cannot feel at the event horizon eventually becomes severe enough to disrupt the most tightly bound structures in nature. Whether it reaches a literal singularity, a genuine point of infinite compression, or whether quantum mechanics intervenes before that point and produces something else, something the equations of general relativity cannot see, is precisely the question that divides the four competing pictures of what exists on the other side. Each of them agrees on the tidal physics. Each of them agrees that general relativity breaks down at some point inside. Where they disagree fundamentally and irreconcilably is what replaces it. And the first of those four answers does not propose a gentler version of the singularity. It proposes that the singularity never forms at all, that the collapse reaches a density so extreme, not infinite, but the most extreme density quantum mechanics permits, and then stops and bounces. Not metaphorically, physically. The compressed matter rebounds outward, and what was falling in becomes something moving the other direction. The question is what that something emerges into, and whether anything outside the black hole would ever know it happened. There is a thought experiment that sounds straightforward until you work through the physics. Replace the sun with a black hole of identical mass, one solar mass, compressed to a sphere roughly 3 kilometers across, smaller than most city parks, and ask what happens to Earth. The answer most people expect is immediate catastrophe. The answer the equations actually give is considerably stranger. Earth's orbit would not change. Not immediately. Not at all. In fact, for as long as the distance remains the same. Gravity depends on mass and distance, not on whether the mass is a burning sphere of plasma or a point of collapsed spacetime. The curvature of spacetime that keeps Earth on its roughly circular path around the Sun is determined entirely by how much mass sits at the center and how far away Earth sits from it. Change the form of that mass without changing its quantity, and the orbit continues as before. What changes is everything else. 8 minutes after the Sun became a black hole, the time it takes light to travel, 150 million kilometers, the sky would go dark. Not dim, dark. The stars would appear immediately, sharper than anyone alive has ever seen them, because the atmosphere would no longer be scattering solar light. Within a week, the global average temperature would drop below -70 degrees Celsius. Within a year, it would approach -240 colder than the surface of Pluto, colder than anywhere in the inner solar system has ever been measured. The oceans would freeze from the surface down in layers, locking under kilometers of ice. The atmosphere would begin to condense and snow nitrogen first, then oxygen settling as a thin crystalline layer across the frozen continents. The planet would still be there, still orbiting, geometrically intact, simply no longer capable of sustaining any chemistry that requires liquid water or atmospheric pressure or temperatures above the freezing point of most compounds. A frozen marble tracing the same ellipse it always has, around a point of gravity that no longer produces any light. That is the calm version of the scenario, the one where distance is preserved. The dangerous version begins when Earth moves closer, and here the inverse square relationship of gravity becomes the central fact. Halve the distance to a gravitational source, and the pull on any given point quadruples. Reduce the distance to 1/10, and the pull increases 100-fold. More importantly, for a planet with a diameter of nearly 13,000 kilometers, the difference in pull between the near side and the far side, the tidal gradient, grows dramatically as distance shrinks. At the current distance between Earth and Sun, that gradient across Earth's diameter is negligible. Move Earth 10 times closer to a 1 solar mass black hole, and the tidal gradient across that same diameter becomes strong enough to deform the planet's shape measurably. There is a moon of Jupiter, called Io, that demonstrates what tidal heating does at moderate intensity. Io orbits Jupiter at a distance of roughly 420,000 kilometers, about the same as Earth to Moon, but its orbit is kept slightly elliptical by gravitational interactions with two other large moons. That ellipticity means Io is sometimes closer to Jupiter and sometimes farther, and as it moves, the tidal gradient across its interior flexes it, compressing and stretching the rock slightly with each orbit. That mechanical flexing converts to heat through friction. The result is a moon with no impact craters because its surface is too geologically active to preserve them. Sulfur volcanoes erupting continuously, lava lakes hundreds of kilometers across, plumes reaching 500 kilometers into space. Io is, by any measurement, the most volcanically active body in the solar system. And it gets there not from radioactive decay or residual formation heat, but from the gentle, repetitive squeeze of orbital geometry. Scale that mechanism by several orders of magnitude. An Earth-sized planet approaching a stellar mass black hole would begin to experience tidal heating long before the gravitational gradient became strong enough to pull it apart. The crust, which floats on a partially molten mantle, would flex with increasing amplitude as the tidal forces grew. The friction generated in the mantle would raise internal temperatures. Magma chambers would pressurize and rupture, not in the localized way of a volcanic eruption, but across multiple points simultaneously, as the entire planetary interior responded to the tidal cycle. The oceans, meanwhile, would be pulled into tidal bulges orders of magnitude larger than anything the moon produces, not meters of variation, but swells hundreds of kilometers high, sweeping across the surface as the planet rotated into and out of the tidal axis. At a certain critical distance called the Roche limit, the point at which the tidal gradient across an object exceeds the self-gravity holding it together, the planet stops being a planet. For a body the density of Earth orbiting a 1 solar mass black hole, that limit lies at roughly 9,000 kilometers from the center. Inside that distance, the tidal forces pulling the near side inward exceed the gravity pulling the planet together, and the structure begins to disintegrate. Not all at once, the process takes time, the debris spreading into a thin arc that circles the black hole, colliding with itself, heating through compression and friction until it glows. The iron that made Earth's core, the silicon that made its mantle, the oxygen and nitrogen that made its atmosphere, all of it becoming plasma, ionized gas in a disk rotating at a fraction of the speed of light, radiating at temperatures of millions of degrees. What was a planet becomes an accretion disk. What was an orbit becomes a slow inward spiral. There is an angular momentum consideration here that most treatments of this scenario skip over. The debris doesn't fall straight in. It retains the rotational energy of the planet's original orbit, and that energy keeps it circling, but in an orbit that decays over time as the plasma radiates energy away electromagnetically. Some fraction of the infalling material gets redirected by the black hole's magnetic field and ejected perpendicular to the disk in narrow jets moving at relativistic speeds. The atoms that made up the crust of a planet could, in this way, end up propagating outward through interstellar space at close to the speed of light, seeding distant regions of the galaxy with heavy elements. There is a narrow regime, extremely narrow, where a planet at the right distance from a rapidly spinning black hole might receive enough radiation from the accretion disk to maintain surface temperatures above freezing without receiving enough tidal stress to structurally fail. The energy source would not be sunlight. It would be X-rays and high-energy ultraviolet radiation from infalling gas, a harsh and variable illumination nothing in Earth's biology has ever adapted to. Whether any chemistry capable of self-replication could persist under those conditions, shielded by a sufficiently thick atmosphere or a strong magnetic field, is genuinely unknown. The physics permits it in principle. The biology is an entirely open question. What this scenario clarifies, more than anything else, is how precisely calibrated Earth's current situation actually is. Not just the distance from the Sun, but the Sun's mass, its stability, the nearly circular shape of Earth's orbit, the presence of a large moon producing tidal forces gentle enough to drive ocean mixing without deforming the crust. Every one of those parameters sits within a range that permits the particular chemistry we call life. Move any of them significantly, and the range collapses. A black hole makes that visible in a way a stable star does not, because it removes the light and leaves only the gravity, and gravity alone, it turns out, is not enough. Which raises a question the tidal physics here cannot answer. If a planet's structural integrity depends on being far enough away from the tidal gradient, and a star's structural integrity depends on the same, then what happens when the object falling toward the black hole is not a planet or a star, but the theoretical maximum density that matter can reach before the equations of general relativity stop working entirely? What happens at the center is not a question about tidal forces. It is a question about whether matter has a flaw. The Sun contains 99.8% of all the mass in the solar system. Everything else, the 8 planets, their moons, the asteroid belt, the Kuiper belt, the scattered disk, the entire Oort cloud, with its hundreds of billions of comets, amounts to the remaining 0.2%. The Sun's gravitational dominance over this system is not partial. It is nearly total. Every orbit, every trajectory, every stable path any object in this system follows is defined by the curvature of spacetime produced by that central mass. Now compress that mass into a sphere 3 kilometers across. Not reduce it, compress it. The same quantity of matter, the same gravitational influence at any given distance, the same curvature of space-time at 150 million kilometers. Just no longer a burning plasma held up by radiation pressure. Just mass collapsed past every structural limit, contained within a boundary from which nothing moves outward. Earth's orbit does not change. Not by a meter, not by a millisecond of orbital period. This surprises people, and it shouldn't, but the surprise is worth examining because it reveals something important about what gravity actually is. Gravity, in general relativity, is not a signal emitted by mass. It is not something the sun broadcasts outward the way it broadcasts light. It is the shape of space-time in the region surrounding the mass, a shape that was established by the mass being there, and that persists regardless of what form that mass takes. Replace the sun with a black hole of identical mass, and the shape of space-time at Earth's distance is identical. The orbit continues because the geometry that produces the orbit has not changed. What changes is everything the sun was doing beyond simply sitting there with mass. 8 minutes after the transition, the time it takes light, traveling at 300,000 kilometers per second to cross 150 million kilometers, the sky goes dark. Not dim. Completely dark. The photons that left the sun's surface 8 minutes ago are the last ones that will ever arrive. The stars appear immediately, with a clarity no human alive has experienced, because the atmosphere is no longer scattering solar light. The band of the galaxy stretches overhead, visible at what would have been noon. For approximately 40 seconds, the view is extraordinary. Then the temperature begins to drop. Earth's surface temperature is maintained almost entirely by absorbed solar radiation, roughly 1,360 watts per square meter arriving at the top of the atmosphere. Without it, the planet begins radiating its stored heat into space faster than any remaining source can replace it. Within a week, the global average drops below -70 degrees Celsius, colder than Antarctica in winter, sustained everywhere simultaneously. Within a year, it approaches -240 degrees, a temperature at which carbon dioxide freezes out of the atmosphere and settles as dry ice on the surface. The nitrogen follows eventually. Then the oxygen. The air itself precipitates layer by layer until the surface pressure approaches vacuum. The oceans freeze from the surface down, which takes longer than most people expect. Water has a high specific heat. It stores thermal energy efficiently and releases it slowly. The surface freezes within weeks, but the deep ocean, insulated by kilometers of ice above it, retains heat for centuries. Near hydrothermal vents, fissures in the ocean floor, where geothermal heat drives water temperatures above 90 degrees Celsius. Regardless of what happens at the surface, the chemistry that sustains life continues. Earth releases roughly 47 terawatts of heat from its interior, generated by the radioactive decay of uranium, thorium, and potassium in the mantle and crust. 47 terawatts sounds substantial, until you note that the sun delivers approximately 170,000 terawatts to Earth's surface. The geothermal contribution is less than 3/10,000ths of what solar radiation provides. It is enough to keep isolated ecosystems alive near the vents. It is not enough to warm a planet. Looking toward where the sun used to be, something faint and strange would be visible. A one solar mass black hole has a photon sphere, the radius at which light orbits, rather than escaping, at roughly 4.4 kilometers from the center. The event horizon itself sits at about 3 kilometers. These are distances smaller than most towns. But the gravitational lensing effect, the bending of background starlight around the black hole's edge, would produce a faint distortion in the star field at that position, a slight brightening ring where light from behind the black hole is bent around it. Not dramatic. not the glowing orange ring from images of supermassive black holes, which are surrounded by vast accretion disks of infalling gas at millions of degrees. A solar mass black hole replacing the Sun would have no accretion disk to speak of, because the planets do not spiral inward, they continue orbiting. There is no gas to consume. There is no radiation from the object itself. Just a subtle warping of the stars behind it, marking the location of 3 kilometers of compressed mass. The solar system's long-term stability under this scenario is more complicated than the immediate picture suggests. Currently, the Sun exerts a small but non-negligible outward pressure on the planets through its solar, wind, and radiation pressure. Remove those, and the gravitational balance shifts slightly, not enough to immediately destabilize anything, but enough to alter the slow secular evolution of the orbits over billions of years. Jupiter and Saturn, whose combined mass accounts for most of that remaining 0.2%, exert gravitational perturbations on the inner planets that play out over timescales of millions to tens of millions of years. The current configuration of the solar system has been shown to be chaotic. In the technical sense, small perturbations amplify over long timescales, and removing the Sun's non-gravitational forces changes the baseline of that calculation. Whether Earth's orbit remains stable over billions of years or eventually drifts into a configuration that sends it either escaping the system or spiraling inward is not a question with a clean answer. The timescales involved are long enough that other factors, stellar flybys, the gradual decay of the black hole through Hawking radiation, which for a solar mass black hole would take approximately 2 × 10⁻⁶ years, far longer than the current age of the universe by 57 orders of magnitude, become relevant. What this scenario clarifies, more precisely than almost any other thought experiment, is the distinction between gravity and light. We experience them as arriving together from the same source, and it is easy to conflate them, to think of the Sun as a single object, providing both the warmth that sustains life and the gravitational anchor that shapes the solar system. Replace the Sun with a black hole of equal mass, and those two functions separate completely. The gravitational function continues unchanged. The light function stops instantly. The solar system persists. Life does not. Which points towards something the tidal physics and the orbital mechanics both avoid addressing directly. If a black hole of one solar mass, 3 kilometers across, producing no light, exerting no radiation pressure, can maintain a stable solar system indefinitely while making it completely uninhabitable, then the question is not whether gravity alone can organize a planetary system. It clearly can. The question is what, if anything, exists at the center of that 3-kilometer object, and whether the process that compressed a star's worth of mass into that volume left anything on the other side, or simply ended there. In the autumn of 2008, a tunnel, 27 kilometers in circumference, buried 100 meters beneath the French-Swiss border, was switched on for the first time. The newspapers that week were not primarily interested in the physics. They were interested in the possibility that the machine might end the world. The fear was specific, that colliding protons at high enough energies might produce a microscopic black hole, and that this black hole, instead of vanishing, might slowly consume the Earth from the inside out. Courts in multiple countries received lawsuits attempting to halt the experiment. Physicists received death threats. The question was taken seriously enough that independent teams spent years producing formal safety assessments before the first collision was ever run. The assessment concluded the fear was unfounded. But the reasoning behind that conclusion is more interesting than the conclusion itself because it touches directly on what it would actually take to manufacture a black hole, and why that number is so far beyond any technology that exists or is likely to exist that the gap is difficult to express in ordinary language. Start with what a black hole requires at the most basic level. A quantity of mass or energy must be compressed within its own Schwarzschild radius, the distance from its center at which the escape velocity reaches the speed of light. For a black hole the mass of the Sun, that radius is about 3 kilometers. For a black hole, the mass of a single proton, roughly 1.67 times 10 to the negative 27 kilograms, the corresponding Schwarzschild radius is approximately 10 to the negative 54 meters. To put that in terms of something measurable, a proton itself is about 10 to the negative 15 meters across. The Schwarzschild radius of a proton's mass is 39 orders of magnitude smaller than the proton. Compressing a proton's worth of mass into a true black hole would require squeezing it into a volume so small that it makes the proton look, by comparison, approximately as large as the observable universe looks compared to a grain of sand. The energy required to achieve that compression is called the Planck energy, roughly 1.9 times 10 to the 9th joules, or about 10 to the 19th giga-electron volts. The collider in Switzerland operates at 13 tera-electron volts, which is 13 times 10 to the 12th electron volts. The Planck scale is 10 to the 19th giga-electron volts, which is 10 to the 28th electron volts. The gap between what the collider produces and what a black hole requires is a factor of roughly 10 to the 15th 1 quadrillion. If the collider were a single step in a staircase, the Planck scale would be about 10,000 light years above it. There is a caveat, and it deserves honest treatment. Certain theoretical frameworks, ones that propose the existence of extraspatial dimensions beyond the 3 we experience, suggest that gravity might be stronger at very short distances than general relativity predicts, because it spreads into those additional dimensions. If that were true, the effective Planck scale would be lower, and the energy required to produce a microscopic black hole would be reduced. Some versions of this idea brought the threshold down to ranges that might, in principle, be accessible to a sufficiently powerful collider. This was the theoretical basis for the concern in 2008. It was not a fringe idea, it was a legitimate consequence of serious theoretical physics, taken seriously by serious physicists. The reason the concern did not translate into actual danger is a separate argument, and it comes from somewhere unexpected. Earth's atmosphere is continuously bombarded by cosmic rays, high-energy particles produced by supernovae, gamma-ray bursts, and other violent astrophysical processes. These particles strike air molecules at energies that, in some cases, exceed the collider's output by factors of tens of millions. The most energetic cosmic ray ever detected, recorded in 1991 and now called the Oh My God particle, carried roughly 3 times 10 to the 20th electron volts, about 40 million times the collider's maximum energy. When that particle hit a nitrogen nucleus in the upper atmosphere, the collision energy dwarfed anything the collider has ever produced. The same collisions, at similar or greater energies, have been occurring on Earth, on the Moon, on every rocky body in the solar system for billions of years. If high-energy particle collisions could produce dangerous black holes under any physical conditions, the solar system would have been destroyed long before the Sun finished forming. The Moon has no magnetic field and no atmosphere to deflect cosmic rays. Its surface has been exposed to direct bombardment for 4.5 billion years at energies vastly exceeding anything the collider achieves, it still exists. That existence is itself an experimental result. But the question of whether microscopic black holes could form at the collider is genuinely interesting, independent of the safety question, because the answer would tell us something fundamental about gravity at short distances. If a microscopic black hole did form in a collision, even one lasting 10 to the negative 26 seconds before evaporating, it would leave a specific signature in the detector data. A black hole, unlike a conventional particle decay, has no preferred direction. It radiates in all directions with equal probability, producing what physicists call an isotropic spray of particles with a thermal energy distribution. Conventional particle decays are highly directional, governed by specific quantum numbers and conservation laws that make their decay products asymmetric. The two signatures look completely different in the detector. Every collision the machine has run, and it has recorded hundreds of billions of them, has been searched for exactly this pattern. None has been found. That absence is not a failure. It is a measurement. Each run of the collider tightens the constraints on what extra-dimensional theories are still viable, which combinations of additional dimensions and energy scales remain consistent with observation, and which have been ruled out. The machine is not just smashing protons together looking for new particles. It is mapping the boundary of what the known laws of physics predict, and searching for the places where that map develops edges. There is something worth sitting with in that framing. The collider was designed to answer questions about the Higgs mechanism, why particles have mass, and about the conditions that existed in the first fractions of a second after the universe began. In 2012, it found what it was looking for, a particle with the properties the theory had predicted for nearly 50 years. But it was also designed to find the unexpected, to run at energies where new physics might appear that no theory had anticipated. The absence of microscopic black holes in the data is itself a constraint on quantum gravity, which has no other confirmed experimental test. The machine is, among other things, the only instrument humanity has built that is even beginning to approach the energy scales where gravity and quantum mechanics might disagree. Which returns the question to where it started, not to whether a black hole can be made on Earth, but to what the mathematics of black holes says about what exists inside one. The collider cannot produce a black hole, but the same quantum mechanics that explains why it cannot, the Hawking evaporation process, the uncertainty principle, the behavior of spacetime at Planck scales, is precisely the physics that the four competing theories invoke when they describe what happens at the center of the black holes that do exist. The machine in Switzerland and the singularity at the center of a collapsing star are asking the same question from opposite ends of the energy spectrum. What does quantum mechanics do to gravity when the two cannot be separated? There are roughly 100 million black holes in the Milky Way. That estimate comes from counting the massive stars that have existed long enough to exhaust their fuel and collapse, and from what we understand about how much of that collapse results in a black hole rather than a neutron star or a complete dispersal of the stellar material. 100 million is a lower bound, not a ceiling. The actual number is probably higher. Of those 100 million, we have directly confirmed the existence of a few dozen. The discrepancy is not because the rest don't exist. It's because a black hole with nothing to eat produces no light, no X-rays, no radio emission, no signal of any kind that our instruments are designed to detect. Every detection method we developed over the 20th century depended on a black hole consuming something gas, a companion star, a passing cloud of matter and radiating energy as that material heated and spiraled inward. A black hole sitting quietly in empty space, orbiting nothing closer than a stable stellar companion at a safe distance, is for all practical purposes completely invisible to every telescope ever built. Which meant that for most of the history of black hole astronomy, we were looking at only the hungry ones. In 2022, a different kind of detection became possible. A space mission designed to map the positions and motions of roughly 1.8 billion stars with extraordinary precision, measuring each star's location to within 10 micro-arcseconds, an angular resolution equivalent to resolving a coin sitting on the surface of the Moon from Earth, had accumulated enough data over enough years to detect something subtle. Not radiation, not heat, motion. A star in the constellation Ophiuchus, roughly 1,600 light-years away, about 1% of the Milky Way's diameter, close enough that if the galaxy were scaled to the size of the continental United States, this star would be sitting roughly 3 kilometers from us, was moving in a way that didn't fit a single isolated object. Its path through space was not a straight line. It was wobbling, periodically, in a pattern consistent with orbital motion around an unseen companion. The wobble repeated every 185 days. The amplitude of the wobble implied the companion had a mass of roughly 10 times the Sun. No light, no X-rays, no heat signature of any kind. Just the gravitational presence of 10 solar masses, detectable only through the effect it exerted on the star next to it. The object was designated Gaia BH1. At 1,600 light-years, it became the closest confirmed black hole to Earth ever found. Working out what the object actually is requires treating the companion star as a measuring instrument. The star's orbital velocity, how fast it moves around the common center of mass, can be measured by watching the Doppler shift of its spectral lines, the way the wavelengths of light from the star compress slightly as it moves toward us and stretch as it moves away. Combining the orbital period, the velocity amplitude, and the geometry of the orbit yields what astronomers call the mass function, a quantity that sets a minimum on the mass of the unseen companion. For Gaia BH1, that minimum came out at roughly 9.6 solar masses. The theoretical upper limit for a neutron star, the densest form of matter capable of holding itself up against further collapse, is about 2.3 solar masses, possibly a little higher, depending on the equation of state of nuclear matter at extreme densities. No neutron star anywhere near 9.6 solar masses is consistent with any known physics. The only object that can be that massive, that compact, and produce no detectable radiation is a black hole. The argument closes without a gap. What makes Gaia BH1 genuinely difficult to explain is not its existence, but its survival. When a massive star ends its life, it does not simply collapse quietly into a black hole. It explodes a core collapse supernova that, for a few weeks, outshines the entire galaxy it lives in. The explosion is not spherically symmetric. It is asymmetric, which means the remnant, the newly formed black hole, receives a kick, a natal velocity imparted by the uneven ejection of matter. These kicks can be hundreds of kilometers per second. For a binary system to survive this event, the explosion must be weak enough, or the kick directed in just the right way, that the companion star is not flung away into independent orbit. The two objects must remain gravitationally bound after the explosion. That Gaia BH1 exists in a stable binary with a sun-like star means the original supernova was either unusually gentle or the kick happened to be directed along the orbital plane in a way that preserved the system. Both scenarios are possible. Neither is common. The system has been in its current configuration for somewhere between tens of millions and a few billion years, depending on the initial mass of the star that became the black hole and how long it took to exhaust its fuel. Long enough that the companion star has evolved normally, showing no anomalous chemistry or rotation that would suggest a troubled history. Long enough that the black hole has had no material to consume and has simply sat there, silent, while the galaxy completed most of a full rotation around its center. The detection raises a straightforward but uncomfortable implication. If one dormant black hole in a quiet binary system exists 1,600 light-years away and was invisible to every detection method except one that only became available recently, then the question is not how unusual Gaia BH1 is. The question is, how many more exist at similar distances, in similar configurations, that the same method will find as more data accumulates? The current mission has observed roughly 1% of its total planned observing time. Estimates suggest there may be hundreds of similar systems within a few thousand light-years dormant black holes in stable binaries, carrying no accretion disk, producing no radiation, identifiable only through the orbital wobble they induce in a companion. We happen to be watching carefully enough. The galaxy we thought we understood, mapped by light, catalogued by emission, surveyed by the radiation of active processes, sits inside a darker galaxy we are only beginning to see. The visible structure, all the stars and gas and dust that optical and radio telescopes have spent a century mapping, is threaded with dark remnants that emit nothing. Their mass is there, shaping orbits, bending light slightly, contributing to the gravitational field that holds the spiral arms together. But they leave no photon trail. The only way to find them is to watch the stars next to them long enough to notice the wobble. Gaia BH1 is not remarkable because it is dangerous. At 1,600 light-years, its gravity affects nothing in the solar system. Its companion star orbits it at the same distance Earth orbits the Sun, and does so stably, year after year, as it has for millions of years. It is remarkable because it represents a category dormant, invisible, gravitationally present that almost certainly vastly outnumbers the black holes we can see, the ones we built entire detection networks to find, the ones producing X-rays and jets and accretion signatures, may be a small and unrepresentative minority. Most of the black holes in the galaxy, on this picture, look like nothing at all. They are detectable only as absences, a mass that doesn't shine, a companion that moves in a curve when it should move in a line, a gravitational signature without a luminous source. Whether any of them are close enough for their gravity to affect the solar system in any meaningful way, over any timescale relevant to human concerns, is a question the next several years of data will begin to answer. What is already clear is that the census of nearby black holes was, until very recently, almost entirely blank. And the first entry in that census was found not by looking for black holes, but by looking for stars that were moving in ways that required one to be there. Stellar physics has a ceiling. It is not arbitrary, it follows directly from the physics of what happens inside a massive star when its core runs out of fuel and the pressure that held everything up disappears. As the core collapses and temperatures climb past a certain threshold, The gamma rays produced in the implosion become energetic enough to spontaneously convert into electron-positron pairs matter and antimatter created directly from light. This pair production absorbs energy from the collapse rather than resisting it, which destabilizes the core catastrophically. The result is not a controlled collapse into a black hole. It is a complete disruption, the entire star blown apart in an explosion so thorough that nothing is left behind. No remnant. No neutron star. No black hole. Just expanding debris. This process pair instability supernova creates what astrophysicists call the pair instability gap, a range of masses between roughly 50 and 120 solar masses, where black holes should not be able to form from a single collapsing star. Stars that die within that mass range should destroy themselves completely before any remnant can hold together. The ceiling below the gap is around 40 to 50 solar masses. The floor above it is around 120, where the explosion is energetic enough to blow away the outer layers, but the core is massive enough to collapse into a black hole anyway. Between those two values, roughly 50 to 120 solar masses, the theory says there should be nothing. In late 2019, a measurement appeared that seemed to place a black hole squarely inside that gap. A star in our galaxy, roughly 3,000 light-years away, about 2% of the Milky Way's diameter, a relatively close neighbor, was observed wobbling with a period of 78 days around an unseen companion. The wobble amplitude implied the companion had a mass of roughly 70 solar masses. The companion produced no light, no X-rays, no detectable radiation of any kind. 70 solar masses of invisible mass sitting inside the pair instability gap, in a galaxy where the pair instability gap was supposed to be empty. The results circulated quickly and generated genuine alarm among people who study stellar evolution. Not alarm in a social sense, alarm in the technical sense that a well-confirmed theoretical framework was apparently contradicted by a clean, direct observation. If a 70 solar mass black hole could form from a single collapsing star, either pair instability physics was wrong, or there was some formation pathway that had been overlooked, or the measurement was mistaken. All three possibilities were taken seriously simultaneously, which is what the situation warranted. The measurement turned out to be mistaken, but in an instructive way. The system, designated LB1, contained not one star, but two. The visible star doing the wobbling was a rapidly rotating B-type star, roughly 8 solar masses, with a broad emission spectrum. Sitting nearby was a second star, a fainter object, whose spectral lines were partially blended with the first star's light in the original data. When the two spectra were disentangled carefully, using higher resolution follow-up observations and improved modeling of the B star's rotation profile, the inferred mass of the dark companion dropped dramatically. Not 70 solar masses, closer to 10. A perfectly ordinary stellar mass black hole, well below the pair instability gap, in a binary system whose geometry had been misread. The pair instability gap remained intact, but something more interesting had emerged from the episode. Because the same year LB1 was being reanalyzed, a gravitational wave detection was published that did place two black holes inside the pair instability gap, not from direct stellar collapse, but from merger. Two black holes, with masses of 85 and 66 solar masses respectively, both sitting inside the forbidden range, were detected spiraling together and merging into a remnant of 142 solar mass. That remnant, at 142 solar masses, falls into the range called intermediate mass black holes, objects more massive than the stellar mass black holes formed by individual stars, but far less massive than the supermassive black holes anchoring galactic centers. Intermediate mass black holes had been theorized for decades and confirmed almost nowhere. This was the first clean detection. The 85 and 66 solar mass components could not have formed from individual stellar collapse under standard conditions. The pair instability mechanism would have prevented it, which means they must have formed some other way. The most likely explanation involves hierarchical mergers inside dense stellar environments, globular clusters, nuclear star clusters, the crowded cores of young massive stellar associations. In these environments, stellar mass black holes form from individual stars in the normal mass range, below the pair instability ceiling. But the density of the cluster is high enough that black holes encounter each other, pair into binaries, and merge. The merger product has more mass than either parent. If it remains in the cluster rather than being ejected by the gravitational recoil kick from the asymmetric merger, it can merge again and again. Each generation of merger pushes the product higher in mass through the pair instability gap that stellar evolution cannot cross until objects appear that no single star could ever have produced. This is a significant revision to the picture of how black holes evolve. The standard model treats black holes as static end products. A star collapses, a black hole forms, and the black hole then sits there, perhaps accreting slowly, for the remaining life of the universe. The hierarchical merger scenario makes them dynamic participants in an ongoing process. Black holes in dense clusters grow by merging with each other, building mass through repeated collisions over timescales of millions to billions of years. The mass distribution of black holes in the universe is not just a record of which stars have died, it is a record of which black holes have found each other. There is a further implication that connects directly to the question of what black holes contain. When two black holes merge, the remnant is not simply the sum of its parents. Some fraction of the total mass, typically a few percent, is radiated away as gravitational waves during the final inspiral and merger. For a merger, producing a remnant of 142 solar masses, the energy radiated in gravitational waves during the final fraction of a second was equivalent to roughly 8 solar masses converted entirely into spacetime ripples. 8 times the mass of the Sun, released not as light or heat or particle radiation, but as pure oscillation in the geometry of space, spreading outward at the speed of light. By the time those waves reached detectors on Earth, roughly 17 billion light-years away, they had stretched and compressed the distance between the detector's mirrors by less than 1/10,000th of the fine mirror's billion width of a proton. That measurement was made successfully. What the merger does not answer is what the interior of the remnant contains. A 142 solar mass black hole formed by merger carries the same external description as one formed by stellar collapse. It is characterized entirely by its mass, its spin, and its electric charge, which is effectively zero for any astrophysical object. Its interior is as inaccessible as any other black hole's interior. Whether the singularity it contains is structurally different from one formed by a single collapsing star, whether the quantum state of the merged remnant retains any information about the two objects that produced it, whether the pair instability physics that prevented its formation by any other route leaves any trace inside it, these questions are not answerable from the outside. The merger tells us how it formed. It tells us nothing about what exists at its center. That question, what occupies the interior of a black hole, formed not by stellar collapse, but by the repeated merger of objects that were themselves already black holes, sits at the edge of what any current theory can address. And it points toward a larger puzzle. If black holes can grow by merging with each other, starting from stellar mass objects and building upward through the pair instability gap, the question becomes how far that process can go, and whether the most massive black holes known, the ones anchoring entire galaxies at masses of billions of solar masses, could have grown partly through this mechanism, or whether something else entirely produced them. The universe has a speed limit for black hole growth. It is not an arbitrary rule, it follows from the physics of accretion itself. As a black hole consumes surrounding gas, that gas heats up as it falls inward and radiates. The radiation pushes outward on the infalling material. At a certain accretion rate, the outward radiation pressure exactly balances the inward gravitational pull, and the black hole can no longer consume faster regardless of how much material surrounds it. This limit is called the Eddington rate, named for the relationship between a black hole's mass and the maximum luminosity it can sustain without blowing its own fuel supply away. A black hole accreting at the Eddington rate can roughly double its mass in about 45 million years. That sounds fast until you note what the observations are asking it to explain. The universe, at a redshift of roughly 7.5, was about 700 million years old. Not 700 million years after the first stars, 700 million years after the Big Bang itself. At that moment, which we observe today by catching the ancient light that has spent most of the universe's lifetime traveling toward us, there existed black holes with masses exceeding 1 billion solar masses. 1 billion solar masses. Starting from the first stars, which formed perhaps 200 million years after the Big Bang and could produce black holes of perhaps a few hundred solar masses when they died. A black hole, accreting continuously at the Eddington limit for the entire available time, 500 million years, could reach at most a few tens of millions of solar masses. To reach 1 billion, it would need to have accreted faster than the Eddington limit allows, started from a much more massive seed, or both. TON 618 makes that problem considerably worse. It sits 10.4 billion light-years away, which means we observe it as it existed when the universe was roughly 3 billion years old. At that age, it already contained 66 billion solar masses. 66 billion. If the Milky Way's central black hole, 4 million solar masses, were a single coin, TON 618 would be a stack of coins reaching 16.5 kilometers into the sky. It is not the largest number we encounter in cosmology, but it is perhaps the most difficult to explain, because the universe had less time to build it than the standard growth mechanisms straightforwardly allow. The measurement itself comes from the motion of gas. Gas clouds, orbiting a supermassive black hole in the broad line region, a zone extending roughly a light-year from the center, move at velocities set by the gravitational pull of whatever sits at the center. The faster they move, the deeper the gravitational well they are orbiting. Their velocities are readable in the spectrum of the quasar, emission lines from hydrogen and carbon that are broadened by the Doppler shifts of clouds moving both toward and away from us simultaneously, spread across a range of velocities. For TON 618, those velocities exceed 5,000 kilometers per second, about 1.7% of the speed of light. Working backward from that velocity and the size of the emitting region, the implied central mass is 66 billion solar masses. The luminosity of the quasar, 140 trillion times the Sun, is consistent with that mass accreting near the Eddington rate. The two measurements agree. There are currently two broad categories of explanation for how objects like this exist. The first involves the initial seed. If the first black holes in the universe were not formed from individual collapsing stars, which limits the initial mass to a few hundred solar masses, but instead from the direct collapse of massive primordial gas clouds, before star formation could fragment them, the seeds could have been far more massive. A cloud of primordial hydrogen, perhaps 100,000 solar masses, collapsing directly under gravity without pausing to form stars first, could produce a black hole of 10,000 to 100,000 solar masses at formation. Starting from that seed and accreting at the Eddington rate, reaching 66 billion solar masses in 3 billion years, becomes not easy, but at least mathematically possible, without requiring physics that does not exist. The second category involves the accretion rate itself. The Eddington limit assumes a particular geometry and efficiency for how infalling gas radiates. Under conditions of extremely dense, rapid accretion, a regime called super-Eddington accretion, the infalling gas is so thick that the radiation it produces is trapped within the flow rather than escaping to push back against it. The black hole can consume faster than the standard limit for periods that may last millions of years. Both mechanisms probably operated. The question is, which one dominated in which environments and at what epochs? And that question is currently open in a way that is genuinely unsettled rather than merely technically unresolved. What makes TON 618 particularly useful as an object of study is that its quasar phase appears to have ended. The light we receive from it today, the 10 billion-year-old light that has been traveling toward us since the universe was 3 billion years old, shows a bright, active accretion disk. But the variability patterns in that light suggest the feeding rate was already beginning to decline. In the intervening 10 billion years, the gas supply surrounding it has almost certainly been exhausted. The galaxy it inhabits has evolved, its star-forming gas consumed or expelled. TON 618 today, which we cannot observe directly because we are seeing it as it was, not as it is almost certainly dormant. 66 billion solar masses of collapsed spacetime, sitting in darkness at the center of an aging galaxy, consuming nothing, producing nothing, altering the orbits of stars within its gravitational sphere of influence, but otherwise invisible. Its event horizon spans roughly 400 billion kilometers. Light, traveling at 300,000 kilometers per second, would take approximately 15 days to cross from one side to the other. If you were placed at the center of TON 618's event horizon, which is not a physical place but a mathematical boundary, and emitted a light signal in every direction simultaneously, every one of those signals would converge back toward the center rather than propagating outward. The geometry inside admits no outward direction. Whether that geometry connects to anything, whether it terminates at a singularity or transitions into something else, whether the 66 billion solar masses compressed within it left any structure on the other side, TON 618 presents that question at a scale that makes all the smaller versions seem almost comfortable by comparison. There is something worth pausing on in the growth history itself. If TON 618 formed from a direct collapse seed and grew through sustained Eddington rate accretion, the process that built it consumed the equivalent of several entire galaxies worth of gas over 3 billion years. Every atom of that gas that crossed the event horizon added to the mass, deepened the gravitational well, expanded the event horizon outward. The boundary grew as matter fell in, not because something pushed it outward, but because the Schwarzschild radius scales linearly with mass, and mass was accumulating. Each unit of infalling matter enlarged the region from which escape was impossible. The black hole did not consume space. It enlarged the volume of space that consuming it had made inaccessible. Whether anything analogous to the pair instability ceiling that limits stellar mass black hole formation operates at these scales, whether there is some maximum mass beyond which a black hole becomes structurally unstable, or begins losing mass faster than it can gain, it is not currently known. Objects more massive than Ton 618 may exist. Several candidates have been identified in the cores of massive galaxy clusters environments where the infalling gas supply from hundreds of surrounding galaxies never fully exhausts. Whether any of them exceed 100 billion solar masses, and what happens to the interior geometry of a black hole at that scale, is a question the measurements have not yet reached. When a black hole forms, it carries angular momentum. The star that collapsed to produce it was rotating. All stars rotate, and that rotation does not disappear when the star dies. It compresses inward along with everything else, and the resulting black hole spins. If that black hole has a companion, another massive star, orbiting it in a binary system, then over millions of years, as the companion exhausts its own fuel and collapses in turn, the system produces two spinning black holes orbiting each other. Two objects, each containing the compressed remnant of a star that once burned for millions of years, now circling a shared center of mass in silence. No light, no heat, no signal of any kind propagating outward to announce their existence. General relativity predicts that this situation cannot last indefinitely. Any two massive objects orbiting each other, not just black holes, but any pair, emit gravitational waves, oscillations in the curvature of spacetime that propagate outward at the speed of light. These waves carry energy. The energy comes from the orbital motion itself. As the system radiates, the orbit loses energy, and the two objects spiral closer together. The process is extraordinarily slow. At first, a binary system of two 10 solar mass black holes separated by the distance between Earth and Sun would take longer than the current age of the universe to merge through gravitational wave emission alone. But as the separation decreases, the emission rate increases steeply. The power radiated scales with the inverse fifth power of the separation. Halve the distance, and the power output increases by a factor of 32. The in-spiral accelerates. The orbit tightens faster. The objects approach relativistic velocities. In the final fraction of a second before merger, the two black holes are moving at a substantial fraction of the speed of light, separated by a distance comparable to their own event horizons. At that point, the space-time between them is no longer a smooth background through which two objects happen to be moving. It is being violently distorted by two objects whose gravity dominates everything within their vicinity, orbiting so fast that the curvature they produce is changing at a rate comparable to the orbital frequency itself. The gravitational wave emission during this phase, called the merger and ringdown, releases more energy in roughly 1/10 of a second than the Sun will radiate across its entire 10 billion year lifetime. Not comparable energy. Substantially more. Emitted not as light or heat or particle radiation, but as pure oscillation in the geometry of space, propagating outward in all directions at the speed of light. The remnant black hole that emerges from the merger is not simply the sum of its parents. Some fraction of the total mass, typically 1 to 10%, depending on the mass ratio and the spins of the two objects, has been converted into gravitational wave energy and radiated away. For the first merger ever detected, two black holes of roughly 36 and 29 solar masses produced a remnant of about 62 solar masses. 3 solar masses, an amount of matter comparable to 3 times the Sun's entire mass converted entirely into space-time oscillations in approximately 0.2 of a second. The remnant was left spinning rapidly, vibrating at its natural frequency like a struck bell, radiating that vibration away as gravitational waves over the subsequent milliseconds until it settled into a stable, axisymmetric configuration. Physicists call this the ring-down. The detection was made by measuring the change in length of 2 perpendicular 4-kilometer tunnels. When a gravitational wave passes through a region of space, it stretches space in one direction and compresses it in the perpendicular direction simultaneously. The amplitude of this stretching and compressing is characterized by a dimensionless number called the strain, the fractional change in length per unit length. For the first detected merger, originating roughly 1.3 billion light-years away, the strain at Earth was approximately 1 × 10 to the negative 21. 1 × 10 to the negative 21 means that a distance of 1 kilometer changed by 1 attometer, 1 × 10 to the negative 18 meters. A proton is approximately 1 × 10 to the negative 15 meters across. The measurement detected a change in length 1,000 times smaller than a proton across a 4-kilometer baseline. That measurement succeeded. Since that first detection, the catalog has grown to over 90 confirmed events. The majority involves stellar mass black hole mergers, with total masses ranging from a few tens of solar masses to over 140. Several involve neutron star mergers, which produce both gravitational waves and electromagnetic radiation, detectable simultaneously across the spectrum. A handful appear to involve components sitting inside the pair instability mass gap discussed previously, objects that could not have formed from single stellar collapse and must therefore have assembled through earlier mergers. Each detection is a measurement of the merger parameters, the masses, the spins, the distance, the sky location, and through the ring-down a test of whether the remnant behaves as general relativity predicts a Kerr black hole should. So far, every remnant has passed that test. There is a gravitational wave background that these individual detections sit within. The universe contains many millions of black hole binaries at various stages of inspiral, some just beginning to tighten their orbits, some in the slow middle phase, some approaching their final merger. All of them are emitting gravitational waves continuously, at frequencies too low and amplitudes too small to detect individually with ground-based instruments. But collectively, they produce a stochastic background, a gravitational hum permeating the universe, with the loudest contributions coming from the most massive binaries at moderate redshifts. In 2023, multiple independent pulsar timing arrays reported a consistent signal at nanohertz frequencies, gravitational waves with periods of years, detectable through their effect on the precision timing of millisecond pulsars distributed across the galaxy. The signal is consistent with a population of supermassive black hole binaries, pairs of objects each containing millions to billions of solar masses, orbiting each other in the cores of merging galaxies at separations of light years to light months. These are the precursors to mergers that will dwarf anything detected so far. When two supermassive black holes merge, the dynamics are qualitatively different from stellar mass mergers. The inspiral from galactic scale separations to merger scale separations takes hundreds of millions of years. The mechanism that drains the orbital energy changes as the separation decreases dynamical friction from stars and gas at large separations, then gravitational wave emission dominating at small separations. There is a theoretical uncertainty called the final parsec problem. It is not fully clear that the orbital decay proceeds efficiently all the way to merger, or whether something stalls the inspiral at separations of about 1 parsec, roughly 3 light-years. The pulsar timing array detections provide indirect evidence that mergers do eventually complete, since the observed background signal requires a population of systems that reach merger rather than stalling. But the detailed mechanism remains an active area of theoretical work. The gravitational wave energy released in a supermassive black hole merger, 2 objects, each of billions of solar masses, is correspondingly larger than stellar mass mergers by many orders of magnitude. The strain at Earth from such a merger in a nearby galaxy would be detectable not by kilometer-scale instruments, but by space-based ones, with arm lengths of millions of kilometers. A planned space mission with exactly those specifications, arm lengths of 2.5 million kilometers, sensitive to gravitational wave frequencies between 10 to the -4 and 1/10 of a hertz, would directly observe supermassive black hole mergers out to cosmological distances, capturing the full inspiral, merger, and ringdown in detail. If it launches on schedule in the early part of the next decade, it will transform what we know about supermassive black hole demographics, formation history, and the physics of the final parsec. What the gravitational wave data cannot resolve is the interior question. Every merger detected so far has been consistent with general relativity's prediction for how a Kerr black hole should behave, a black hole characterized entirely by mass and spin, with no internal structure accessible from outside. The ringdown tests probe the exterior geometry of the remnant. They confirm the exterior matches the prediction. Whether the interior matches any prediction, whether the singularity general relativity predicts at the center is real, or whether quantum mechanics replaces it with something else, the gravitational wave signal carries no information about that. The waves are generated in the exterior spacetime during the inspiral and merger. Whatever exists inside the event horizon contributes nothing to them. The merger is, from this perspective, the most precise test of general relativity's exterior predictions we have ever performed, and simultaneously the most profound non-answer to the question of what exists inside. Andromeda is approaching. Not metaphorically, physically, measurably, at roughly 110 kilometers per second relative to the Milky Way. That velocity has been confirmed through multiple independent measurement techniques, including the proper motion of individual stars in Andromeda detected by tracking their position against background objects over years of observation. The result is consistent across methods. The 2 galaxies are on a converging trajectory, and the convergence is not a near miss. Gravity modeling of the local group, the loose association of roughly 80 galaxies bound together by mutual gravitational attraction, with the Milky Way and Andromeda as its 2 dominant members, indicates a merger is the expected outcome. The timing, based on current separation and velocity, puts the first close passage at roughly 3.9 billion years from now. 2.5 million light-years currently separates the 2 galaxies. To develop a sense of what that distance means in context, if the Milky Way were compressed to the size of a dinner plate, roughly 30 centimeters across, Andromeda would sit about 6 meters away, roughly the length of a mid-sized room. The 2 plates are moving toward each other at a speed that, at that scale, would cover the 6 meters in something like 150 million years. On human timescales, this is imperceptible motion. On cosmological timescales, it is relatively rapid. The 2 galaxies will close that gap and begin their first gravitational interaction within a period shorter than the time the Sun has already been burning. What happens when they meet is not a collision in any conventional sense. Galaxies are mostly empty space, The average distance between stars in the Milky Way's disk is roughly 5 light-years, about 47 trillion kilometers. When two galaxies pass through each other, the probability that any individual star directly impacts another is extremely small, comparable to firing 2 shotgun blasts at each other from across a continent and expecting the pellets to collide. The stars pass through each other's distributions essentially without contact. What is not empty, and what does interact dramatically, is the gravitational field. Each galaxy acts as a gravitational lens on the other, deflecting stars from their original orbits, stretching populations of stars into long tidal streams, pulling coherent spiral structures apart and redistributing their material. The dark matter halos surrounding each galaxy will interact first. These halos extend far beyond the visible disk. The Milky Way's dark matter halo reaches perhaps 300,000 light-years from the center, roughly 3 times the diameter of the visible disk. Andromeda's halo likely reaches similar distances. At the current separation of 2.5 million light-years, the edges of the two halos are already within gravitational communication. The tidal force each exerts on the other, at that distance, is weak, but not zero. As the separation decreases, halo material from each galaxy will begin interacting, exchanging angular momentum, with some fraction of each halo stripped away into intergalactic space. This dark matter interaction produces no light and cannot be observed directly. Its effects show up in the subsequent stellar dynamics. The first visible consequence will be tidal streams, elongated arcs of stars, pulled from each galaxy's outer disk by the other's gravity during the initial close passage. The Milky Way already has tidal streams from smaller galaxies it has absorbed. The Sagittarius stream, a band of stars stretching nearly completely around the sky, is the remnant of a dwarf galaxy that has been orbiting and gradually disrupting inside the Milky Way's gravitational field for billions of years. The interaction with Andromeda will produce tidal features on a vastly larger scale, streams containing hundreds of millions of stars, arcing across intergalactic space, visible from outside the local group as the structural signature of a major merger. The night sky during and after the first passage would be unrecognizable. Andromeda currently appears as a faint oval smudge in the constellation Perseus, covering an area of sky roughly 6 times the diameter of the full moon, but too faint for most people to notice without dark skies and some experience looking for it. As the separation decreases over billions of years, the apparent size of Andromeda in the sky will grow slowly at first, then accelerating as the close passage approaches. By the time of the first close approach, Andromeda will subtend an angle many times larger than the full moon, its spiral structure visible across much of the sky, the combined effect of its billions of stars producing a diffuse band of light comparable in brightness to the Milky Way itself. After the first passage, as the two galaxies separate temporarily before gravity pulls them back together, the sky will contain both systems simultaneously. 2 massive structures of stars spread across different parts of the celestial sphere, their tidal streams connecting them in arcs of diffuse light. For Earth specifically, the most likely outcome during the merger is displacement rather than disruption. The Sun currently sits roughly 26,000 light-years from the galactic center, in the Milky Way's Orion arm. During a major merger, gravitational perturbations from the interaction can alter the Sun's orbit not by pulling it directly, but by changing the overall gravitational potential that the orbit responds to. Simulations of the merger suggest a non-trivial probability that the Sun ends up in a significantly different orbit in the merged galaxy, perhaps farther from the center, perhaps in a region where the stellar density is lower or higher than the current neighborhood. The direct probability of another star passing close enough to disrupt the solar system's planetary orbits is low, but low is not zero across the timescales involved. A stellar encounter within a few hundred astronomical units could gravitationally perturb the outer planets and destabilize the Oort cloud, sending a cascade of comets into the inner solar system over subsequent millions of years. The more significant constraint on Earth's habitability during this period is the Sun itself. In approximately 4.5 billion years, roughly coinciding with the timing of the merger, the Sun will have consumed enough of its hydrogen fuel that the core will begin to contract and heat, causing the outer layers to expand. The Sun will become a subgiant, then a red giant, its radius expanding to perhaps 150 times its current size, large enough to engulf Mercury and Venus, and to raise Earth's surface temperature well above the point where liquid water can exist. Whether Earth remains in a habitable zone during any phase of the merger depends entirely on timing details that cannot currently be predicted with precision. The collision and the Sun's evolution are happening on overlapping timescales, and the combination makes the future of any life on Earth's surface independent of which astrophysical process one focuses on. At the centers of the merging galaxies, the two supermassive black holes will follow a trajectory that parallels the galactic merger but on a much longer timescale. The Milky Way's central black hole contains roughly 4 million solar masses. Andromeda's contains approximately 140 million, about 35 times more massive. As the galaxies merge, stellar and gas dynamics will gradually bring the two black holes closer together, but the process is not fast. The black holes will first form a wide binary, orbiting each other at separations of tens to hundreds of light years, exchanging energy with surrounding stars through gravitational slingshot interactions. Each star that passes close to the binary and gets ejected carries away a small amount of orbital energy, tightening the binary slightly. As the separation decreases below, roughly 1 parsec, about 3 light years, gravitational wave emission begins to dominate the energy loss, and the inspiral accelerates toward merger. The full process from first galactic contact to black hole merger likely takes 1 to 2 billion years beyond the initial collision. The merger of the two central black holes will produce gravitational waves at frequencies corresponding to the orbital period of the final inspiral periods of years to decades, at nanohertz frequencies. The total energy radiated will depend on the mass ratio and the spins of the two objects, but for a system of this total mass, the gravitational wave luminosity during the final merger will briefly exceed the electromagnetic luminosity of every star in both galaxies combined. The remnant will be a single black hole of roughly 144 million solar masses, spinning rapidly, settling into its final configuration through a ringdown that will be detectable if the appropriate instruments exist at that time across the observable universe. What that remnant contains, whether its interior matches any prediction from theories developed in the early 21st century, or whether the merger of two singularities produces something that neither parent's interior structure anticipated, is a question that the gravitational wave signal from outside the horizon cannot answer. The exterior tells us the mass and spin of the remnant. The interior remains inaccessible by the same geometry that has made every black hole interior inaccessible since the first one formed. Whatever is on the other side of the event horizon of the merged Milky Way Andromeda black hole will be as unreachable as whatever is on the other side of the black holes we can observe today. The merger scales up the question. It does not change it. General relativity does not produce unique solutions. When you write down Einstein's field equations and solve them for a spherically symmetric mass, You get a space-time geometry, the Schwarzschild solution, that describes the curvature of space and time around that mass in all directions and at all times. That solution contains a black hole, a region bounded by an event horizon, inside which all paths lead toward a singularity. But it also contains something else. The mathematics of the solution is time-symmetric. Run it forward, and you get a black hole, a region that matter can enter but never leave. Run it backward in time, and you get the exact opposite, a region that matter can leave but never enter. An object that expels rather than absorbs, that pushes rather than pulls. That is, in every structural sense, the time reverse of a black hole. This object is called a white hole. And the first important thing to say about it is that the mathematics requires it. The Kruskal-Zekera's coordinate system, a way of representing the full Schwarzschild spacetime without the coordinate singularities that make the standard description confusing, shows 4 distinct regions connected at a central point. Region 1 is our universe, the exterior of the black hole. Region 2 is the black hole interior, accessible only by crossing the event horizon inward. Region 3 is a mirror universe, another exterior space-time connected to ours through the geometry, but unreachable without crossing both horizons. Region 4 is the white hole interior, a region from which matter and light can escape into either exterior, but which nothing from outside can enter. The black hole and the white hole in this picture are not 2 separate objects. They are 2 ends of the same geometric structure, connected through what is called the Einstein-Rosen bridge, the wormhole throat that connects region 1 to region 3. The problem is stability. In the classical Schwarzschild solution, the bridge collapses too quickly for anything to traverse it. The white hole region exists in the mathematics, but forms and disappears before any signal can escape from it into the exterior universe. A classical white hole is geometrically real but physically unreachable and unobservable. It exists in the equations the way a solution to a quadratic equation can exist on the negative side of 0, formally correct, physically inaccessible under the conditions of the problem. Where white holes become physically interesting is at the point where classical general relativity breaks down. A black hole that forms from stellar collapse and then slowly evaporates through Hawking radiation eventually reaches the Planck scale, roughly 10 to the negative 35 meters, the scale at which quantum gravitational effects become as strong as all other forces combined. At that point, general relativity alone cannot describe what happens. The evaporation cannot simply continue indefinitely, because that would require the black hole to radiate away more information than quantum mechanics allows to be lost. Something must happen at the Planck scale that resolves the evaporation. One class of proposals developed within the framework of loop quantum gravity, which treats spacetime as a network of discrete quantum units rather than a smooth continuum, suggests that the collapse does not terminate at a singularity. Instead, the compression reaches a maximum density set by quantum geometry and then bounces. The infalling matter, having reached the highest density the quantum structure of spacetime permits, rebounds outward. The object that forms at this maximum compression is sometimes called a Planck star, not a star in the conventional sense, but a configuration of matter at Planck density, the densest state consistent with quantum geometry. From outside the black hole, this bounce is hidden behind the event horizon for an extremely long time, the timescale for Hawking evaporation to reduce the black hole to near Planck mass, which, for a stellar mass black hole, is something in the range of 10 to the 67th years. That is roughly 10 million trillion 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 times the current age of the universe. The bounce happens quickly in the interior time experienced by the infalling matter, possibly in a fraction of a second. But due to extreme time dilation near the Planck density core, that quick interior bounce corresponds to an astronomically long exterior wait. The two timescales are connected by the same gravitational time dilation that stretches all processes near extreme curvature, amplified to its most extreme possible degree. When the evaporation eventually reduces the black hole to near Planck mass, the bounce becomes visible to the exterior. The matter that fell, in which has been in a quantum superposition of infalling and bouncing states for the entire evaporation period, hidden behind the horizon, emerges. The black hole transitions into a white hole phase, a brief, explosive outflow of matter and radiation carrying all the information that originally fell in. The information paradox on this picture is not a paradox at all. The information is preserved throughout, locked inside the Planck star during the long evaporation period, and released in the final white hole explosion. Whether this picture is correct depends on the details of quantum gravity at the Planck scale, which no current experiment can probe. There is, however, a potential observational signature. The white hole explosion at the end of a Planck star's lifetime would release a burst of radiation, the total energy content of whatever originally fell in, compressed into a brief high-energy emission. For black holes that formed in the early universe from density fluctuations shortly after the Big Bang, called primordial black holes, the mass could be small enough that their Hawking evaporation timescale is comparable to the current age of the universe. Some primordial black holes formed with masses of roughly 10 to the 11th kilograms, about the mass of a large mountain, would be completing their evaporation approximately now. Their white hole explosions, if the Planck star model is correct, would produce high-energy gamma-ray bursts of a distinctive character, brief, isotropic, with a specific energy spectrum set by the Planck temperature. The observed population of fast radio bursts, brief, intense radio pulses arriving from cosmological distances with no clear progenitor, has been proposed as a possible candidate, though the match between observations and theoretical predictions remains uncertain. The thermodynamic objection to white holes is serious and deserves honest treatment. The second law of thermodynamics states that entropy, the measure of disorder in a physical system, never decreases in an isolated system. A classical white hole would decrease entropy. It would take a high-entropy state of dispersed radiation and reconstitute it into structured matter emerging coherently from a single point. This is the time reverse of a black hole consuming matter, and just as a broken glass does not spontaneously reassemble, a white hole expelling structured matter seems to violate the arrow of time that thermodynamics defines. The Planck star model attempts to sidestep this by treating the white hole phase not as a time reversal, but as a quantum bounce, a process governed by quantum gravity that is neither purely forward nor purely backward in time, but a superposition that only appears classical in certain limits. Whether this argument fully resolves the thermodynamic objection or merely reformulates it is a question the theory has not settled. What the white hole concept clarifies, regardless of whether it describes anything physically real, is the structure of the information problem. If black holes are purely absorbing objects that eventually evaporate into featureless thermal radiation, the information they consumed is gone. If they are instead transitions, collapse followed by bounce, black hole followed by white hole, then the information is preserved, hidden inside the Planck star during the long evaporation, and ultimately recovered in the final explosion. The two pictures make different predictions about the character of Hawking radiation late in the evaporation process, about the correlations between early and late radiation, and about what the final state of the evaporation looks like. In principle, these predictions are distinguishable. In practice, the timescales involved make direct observation essentially impossible for any black hole formed from stellar collapse. The only candidates for near-term observation are primordial black holes if they exist, if they have the right mass range, and if the instruments sensitive to their final explosion signatures happen to be pointing in the right direction when one completes its evaporation. The white hole is, in this sense, the answer to a question the black hole forces us to ask. Not whether the mathematics permits it, it clearly does, but whether the universe, which appears to respect time asymmetric thermodynamics at every scale we have observed, makes room for the time-symmetric solution that the equations also contain. Whether the other end of the geometry is physically accessible, or whether something in the quantum structure of spacetime permanently closes it off. And if it is accessible, if the Planck star bounce is real, and white holes do form at the end of every black hole's life, then the question of what exists on the other side of a black hole has a specific, testable answer. The same matter that fell in, emerging billions of years later into an exterior universe that may or may not be our own. Ton 618 is not the most dramatic object in the universe because of what it does. It is the most dramatic object in the universe because of what it is. A gravitational well so deep that the numbers required to describe it begin to lose their meaning in ordinary language, and yet every one of those numbers is the direct output of the same equations that describe the black hole at the center of our own galaxy, just scaled by a factor that strains comprehension. Start with the mass. 66 billion solar masses. The Sun contains roughly 2 times 10 to the 30th kilograms. 66 billion suns is roughly 1.3 times 10 to the 41st kilograms. The Milky Way's central black hole, Sagittarius A star, which anchors a galaxy of several hundred billion stars, contains 4 million solar masses. Ton 618 is 16,500 times more massive than that. If Sagittarius A star were represented by a single marble, Ton 618 would be a sphere roughly 25 meters across, about the height of an 8-story building. Both objects are black holes. Both are described by the same Kerr metric, characterized entirely by mass and spin. The physics does not change between them. Only the scale does. The event horizon of Ton 618 spans roughly 400 billion kilometers. Light, moving at 300,000 kilometers per second, would take approximately 15 days to cross from one side to the other. The orbit of Neptune around the Sun has a diameter of about 9 billion kilometers. Ton 618's event horizon is 44 times wider than Neptune's orbit. If this object were placed at the center of our solar system, every planet, every moon, every asteroid in the inner and outer solar system, everything out past Pluto and into the Kuiper belt, would sit inside the event horizon. The nearest stars, Alpha Centauri, 4 light-years away, would still be comfortably outside. But nothing between here and there would retain its current orbit. That scenario is not physically realizable. Ton 618 sits 10.4 billion light-years from Earth, embedded in its host galaxy at a cosmological distance that places it firmly in the early universe. We observe it as it existed when the cosmos was roughly 3 billion years old. It is not moving toward us. It cannot move toward us on any timescale relevant to the solar system's existence. Supermassive black holes do not traverse intergalactic voids freely. They sit at the gravitational centers of massive galaxy clusters, bound by the same large-scale structure that organized the universe after the Big Bang. Moving TON 618 from its current location to our solar system would require transporting 66 billion solar masses across 10 billion light-years of expanding space against the cosmological flow in a time shorter than the current age of the universe. The kinetic energy required for that transport would exceed the total energy output of every star in the observable universe across its entire lifetime. The scenario is, in the most precise sense of the word, impossible. But working through what would happen if it approached is not wasted effort. It is a systematic way of understanding how gravitational influence scales with mass. How the same tidal physics that produces meter-high tides on Earth from the Moon's gravity becomes, at 66 billion solar masses and decreasing distance, a force that restructures entire planetary systems. The sphere of gravitational influence of a black hole, the region within which its gravity dominates over the galaxy's general gravitational field, scales roughly with mass. For Sagittarius A star, that sphere extends a few dozen light-years from the center. For TON 618, it would extend correspondingly farther thousands of light-years. Any stellar system within that sphere would have its orbital dynamics dominated by TON 618's gravity rather than by its own star. Stars would be drawn into elongated, precessing orbits around the black hole. Binary star systems would be disrupted. Planetary systems within the sphere would be gradually destabilized as the dominant gravitational source shifted from their local star to the external mass. At closer range, the tidal effects discussed in earlier acts scale with the inverse cube of distance and linearly with the mass of the source. For TON 618 approaching the solar system, the tidal gradient across the solar system's diameter, roughly 100 astronomical units, about 15 billion kilometers, would become significant at distances of several light-years. That gradient would differentially accelerate the inner and outer solar system, stretching Jupiter's orbit relative to Mercury's, pulling Uranus and Neptune outward relative to Venus and Earth. The orbital resonances that currently maintain stability among the planets, the gravitational relationships that keep Jupiter and Saturn from destabilizing the inner solar system, would break down as the external tidal field, imposed by TON 618, grew stronger than the Sun's own gravitational gradient across those distances. The result would not be a sudden catastrophe, but a slow unraveling, orbits becoming more eccentric, crossing each other over millions of years, eventually ejecting planets from the system or sending them into the Sun. At distances where the tidal gradient across an individual planet's diameter exceeded the planet's self-gravity, the Roche limit, the planet would structurally fail. For Jupiter, with its relatively low density compared to the terrestrial planets, that limit would be reached first. The gas would stream away from the side facing TON 618, forming an elongating plume that curved toward the black hole. That plume would heat through compression and friction, reaching temperatures that cause hydrogen to ionize and radiate. Jupiter's destruction would be luminous, briefly comparable in brightness to a small star, as its mass converted from a gravitationally bound gas giant into a stream of plasma spiraling toward an event horizon 15 days of light travel across. What the accretion of Jupiter's mass would do to TON 618 is essentially nothing measurable. Jupiter contains roughly 1,000th of the Sun's mass, which is 1,000th of one solar mass, which is 1/66 billionth of TON 618's total mass. Adding Jupiter to TON 618 would change its mass by approximately 1 part in 66 trillion. the event horizon would expand by a correspondingly negligible amount. From Ton 618's perspective, to the extent that a black hole has a perspective, Jupiter would be less significant than a single raindrop added to an ocean. This asymmetry is one of the more useful things the thought experiment clarifies. The destructiveness of a supermassive black hole at close range is entirely a function of its tidal forces, not of any active process of consumption. Ton 618 would not need to want to destroy the solar system. The geometry of its gravitational field, extended across the distances involved, would be sufficient. The gravitational lensing signature of Ton 618, were it somehow positioned within a few light years, would be visible to anyone on Earth's surface. The deflection of light around a mass scales with the mass divided by the impact parameter, the closest approach distance of the light ray. For Ton 618, at a distance of 1 light year, background stars near its position in the sky would appear displaced from their actual positions by angles measurable in degrees rather than the micro-arcseconds typical of gravitational lensing at cosmological distances. The Einstein ring, the bright halo of light from sources directly behind the black hole, bent around its edge, would be visible to the naked eye as a luminous ring in the sky with no corresponding bright object at its center. A circle of light sourced from stars and galaxies on the far side, marking the location of 66 billion solar masses of invisible compressed spacetime. The center of the ring would be darker than anything in the sky, not the black of night, but the black of a region from which no light originates and none escapes. What that region contains, what occupies the interior of 66 billion solar masses of collapsed spacetime, is the same question the earlier acts have been building toward. Ton 618's scale does not change the interior question. It amplifies it. If the singularity at the center of a stellar mass black hole represents a failure of general relativity at scales we cannot probe, the singularity at the center of Ton 618 represents that same failure compressed by 16,000 times more mass. Whether quantum gravity resolves the singularity through a bounce, through string-theoretic fuzzball structure, through holographic encoding, or through some other mechanism, none of those proposals depend on the mass of the black hole for their basic validity. They apply to all black holes or to none. Ton 618 is the largest known example of the same question we have been examining since the first act. The answer, whatever it turns out to be, will apply to it as it applies to the 3-kilometer object that would replace the Sun and to the 30-kilometer object 1,600 light-years away, orbiting its quiet companion in silence. There is a black hole 12 billion light-years away that consumes, on average, 1 solar mass of material every day. Not 1 solar mass per year. Not 1 per century. Per day. The Sun contains roughly 2 times 10 to the 30th kilograms. This object is adding that quantity to itself every 24 hours, sustained through a feeding process that has been running for most of the universe's current lifetime. Its total mass sits at approximately 34 billion solar masses, about half the mass of Ton 618, but accumulated through active accretion rather than passive growth, which makes it, by the measure of accretion rate, the most voracious black hole currently known to science. The object is designated J2157. We observe it as it existed roughly 2 billion years after the Big Bang, when the universe was about 14% of its current age. At that epoch, it was the brightest quasar then known, outshining its host galaxy, by a factor that makes the galaxy itself nearly invisible in the glare of the accretion disk. Its luminosity, at the time we observe it, exceeds 10,000 times the combined light output of the Milky Way's several hundred billion stars. That luminosity is entirely a product of the accretion process, matter falling inward, heating through friction and magnetic compression, converting gravitational potential energy into radiation at an efficiency that no other process in the known universe approaches. The efficiency number deserves its own moment. Nuclear fusion, the process powering every star, the reaction that converts hydrogen into helium in the sun's core, converts approximately 0.7% of the rest mass energy of its fuel into radiation. That is the energy source that has sustained the sun for 4.5 billion years and will sustain it for another 5. It is one of the most energetically productive processes that occurs naturally in the universe, and it converts less than 1% of its fuel's mass into energy. Accretion onto a rotating black hole, under optimal conditions, converts between 6 and 42% of the infalling mass energy into radiation. The exact number depends on the black hole's spin. A maximally spinning Kerr black hole achieves the 42% figure, while a non-rotating Schwarzschild black hole achieves about 6%. Even at the lower end, accretion is roughly 9 times more efficient than nuclear fusion. At the upper end, it is 60 times more efficient. This efficiency is why J2157 can outshine a galaxy. Each solar mass of material that spirals into its accretion disk releases, before crossing the event horizon, energy equivalent to somewhere between 6 and 42% of 2 times 10 to the 30th kilograms times the speed of light squared per day. The total power output is not meaningfully expressible in familiar units. The numbers require scientific notation to write and lose their connection to anything experiential long before you finish calculating them. What remains meaningful is the ratio J 2157 at peak activity radiates more energy per second than the entire Milky Way radiates per year. One object, one process, 1 day's worth of fuel, outperforming a galaxy of stars by 4 orders of magnitude. Now, consider what happens when the fuel source is not anonymous infalling gas, but a specific, familiar object, the Sun. The Sun is a sphere of plasma held in equilibrium between 2 opposing pressures, gravity pulling inward and radiation pressure from nuclear fusion pushing outward. It has maintained that equilibrium for 4.5 billion years, fluctuating by less than a fraction of a percent across most of that time. It is, by any reasonable standard, stable. But that stability is conditional. It depends on the gravitational field the Sun sits within being dominated by the Sun's own mass. Introduce an external gravitational gradient large enough to be comparable to the Sun's self-gravity across its diameter, roughly 1.4 million kilometers, and the equilibrium begins to fail. The Sun's diameter is 1.4 million kilometers. Its surface gravity is approximately 274 meters per second squared, about 28 times Earth's surface gravity. The tidal force required to begin distorting the Sun measurably to produce a differential acceleration across its diameter, comparable to its own surface gravity, sets the scale for how close J2157 would need to approach. Given J2157's mass of 34 billion solar masses, that distance works out to roughly several thousand astronomical units, several times the diameter of the solar system's outermost extent. At that distance, The outer layers of the Sun would begin to experience a net gravitational pull toward J2157 that exceeds the pull toward the Sun's own center. The plasma in those outer layers would begin to flow outward, not explosively, but continuously, drawn away from the photosphere in a stream that curves toward the black hole. What follows is the same process we have observed happening to other stars near supermassive black holes throughout the universe, now applied to a star we know intimately. The departing plasma, as it flows toward J2157, retains angular momentum from the Sun's rotation and from the orbital motion of the solar system. It does not fall straight in. It curves into an orbit around J2157, joining an accretion disk that extends inward from thousands of astronomical units to within a few Schwarzschild radii of the event horizon. As successive layers of the disk collide and compress, the temperature rises from the millions of degrees of the Sun's corona to tens of millions of degrees in the inner disk, and potentially hundreds of millions near the innermost stable circular orbit. At those temperatures, the plasma radiates primarily in X-rays and extreme ultraviolet, not in visible light. The accretion disk of a feeding supermassive black hole is not orange or white in the way a star is orange or white. It is a source of ionizing radiation that would strip electrons from atoms at distances measured in light years. For Earth, at its current distance from the Sun, 150 million kilometers, 1 astronomical unit, the relevant question is not what the tidal forces would do to the planet directly. The relevant question is what the radiation environment would do to the atmosphere. Earth's atmosphere is protected from the Sun's current X-ray and ultraviolet output by the ozone layer and, at higher energies, by the magnetosphere. The ozone layer absorbs ultraviolet radiation, effectively up to wavelengths of about 200 nanometers. The magnetosphere deflects charged particles up to energies of a few hundred mega-electron volts. The X-ray flux from J2157's accretion disk at the distances involved would exceed these protective limits by many orders of magnitude. The ozone layer would be destroyed photochemically, ultraviolet and X-ray photons, breaking apart ozone molecules faster than natural processes, can replenish them within a timescale of years to decades. Without the ozone layer, ultraviolet flux at the surface would be lethal to surface life and damaging to oceanic phytoplankton, which produce roughly half of Earth's atmospheric oxygen. The cascade from ozone depletion to ecosystem collapse would proceed on timescales of decades to centuries, well before the tidal forces became directly relevant to the planet's structural integrity. The Sun itself would be completely disrupted long before Earth's structural integrity became the limiting factor. Once the mass loss rate from the solar surface exceeds the rate at which nuclear fusion can replenish the Sun's interior pressure, the Sun begins to deflate. Its radius shrinks as mass departs. The interior temperature and pressure change. The fusion rate adjusts, initially increasing as the core compresses, then eventually dropping as the hydrogen supply depletes faster than gravitational contraction can compensate. The Sun does not explode in this scenario. It unravels a continuous outflow of plasma stretching toward J2157, the stream glowing brightly as it heats and ionizes, the Sun diminishing from the outside inward until the remaining core, no longer massive enough to sustain fusion, collapses into a dense remnant and is itself drawn into the accretion stream. From the perspective of the material falling in, the process is straightforward. It crosses the event horizon, joins the interior of the black hole, and ceases to be observable from outside. From the perspective of someone watching from outside at a safe distance, watching through instruments sensitive to X-rays rather than visible light, the sun appears to approach the event horizon, redden, dim, and freeze at the boundary. The gravitational redshift stretches each photon emitted near the horizon to longer wavelengths, and the time dilation stretches the interval between successive photons. The sun appears not to fall in but to stop an image that persists, fading asymptotically, for as long as the instruments are sensitive enough to detect it. The sun is gone. The image of the sun at the moment of crossing lingers indefinitely. What J2157 does with the sun's mass is add it to 34 billion solar masses of prior accumulation. The event horizon expands by 1/34 billionth of its previous radius. The accretion disk gains 1 additional day's worth of fuel from a source that happened to be a star rather than anonymous gas. The black hole does not distinguish. The physics does not distinguish. 1 solar mass of plasma is 1 solar mass of plasma, regardless of whether it spent 4.5 billion years as the gravitational anchor of a planetary system before falling in. That indifference, the complete absence of any mechanism by which the black hole could treat the sun differently from any other parcel of mass, is perhaps the most clarifying aspect of the thought experiment. The scale of what was destroyed is entirely a human judgment. The physics simply continues. Quantum mechanics has a rule that it treats as non-negotiable. The rule is called unitarity, and it states that the total information content of a physical system is conserved through time. Not approximately conserved, exactly conserved, without exception, in every process quantum mechanics has ever been used to describe. If you know the complete quantum state of a system at one moment, you can in principle reconstruct it at any earlier or later moment. The evolution is reversible. Nothing is truly lost. Every event leaves a complete record in the state of the universe, encoded in the correlations between particles, in the phases of quantum wave functions, in the structure of entanglement across the system. Black holes appear to violate this rule. Not obviously, not immediately, but when you follow the physics carefully through the full life cycle of a black hole, from formation through complete evaporation, you arrive at a conclusion that quantum mechanics says is impossible. The information that fell in does not come back out. The argument runs as follows. A black hole forms when sufficient mass collapses within its own Schwarzschild radius. Everything that subsequently crosses the event horizon is causally disconnected from the exterior. No signal, no particle, no correlation of any kind can propagate from inside the horizon to outside it. The interior is inaccessible to any external observer, not because of technological limitations, but because of the causal structure of space-time itself. Over time, the black hole radiates energy through a quantum process near the event horizon, a process rooted in the behavior of quantum fields in curved space-time. The quantum vacuum near the horizon is not empty in the way flat space-time vacuum is empty. Pairs of quantum fluctuations that would normally annihilate each other can be separated by the horizon. One falls in, one escapes. The escaping particle carries energy away from the black hole, reducing its mass. The process continues until the black hole is gone. The radiation that escapes through this process is thermal. Thermal radiation is the physicist's term for the most disordered possible form of energy, a distribution of particles and wavelengths characterized entirely by a temperature carrying no information about the specific state of whatever produced it. A fire produces thermal radiation. A star produces thermal radiation. The radiation from a black hole, as the calculation predicts it, is also thermal, characterized by a temperature inversely proportional to the black hole's mass, carrying no correlation with the specific quantum state of the matter that fell in. A black hole that consumed a neutron star would produce, according to this calculation, radiation indistinguishable from one that consumed an equivalent mass of hydrogen gas. The specific quantum state of everything that fell in the arrangement of every particle, every spin, every correlation would be absent from the outgoing radiation. When the black hole finishes evaporating, the information is gone. Not hidden, not scrambled into a form difficult to read. Absent in the sense that no measurement of the outgoing radiation, however complete, could reconstruct the initial state of the infalling matter. This is what unitarity forbids, and this is what the straightforward application of the evaporation calculation predicts. The conflict between these two statements, unitarity, requires information to be conserved. Evaporation calculation predicts it is not, is the information paradox. It has occupied a significant fraction of theoretical physics attention for roughly 5 decades, not because it is philosophically interesting, but because it is logically unavoidable. Both sides of the contradiction rest on theories that have been tested to extraordinary precision in every domain where they can be tested. Quantum mechanics has never failed an experimental test. General relativity has never failed an experimental test. Yet their combination, applied to the evaporation of a black hole, produces a contradiction. One of them must be wrong, or incomplete, or both, in a regime we cannot currently access experimentally. There are 4 serious proposals for how the paradox resolves. The first information loss is real, accepts the prediction at face value, and concludes that quantum mechanics must be modified to permit information loss under certain extreme conditions. This is the position that the original evaporation calculation seems to force. It is also the position that most quantum information theorists find unacceptable, because modifying unitarity in any context tends to produce other violations of energy conservation, of the predictive structure of quantum theory that seem even harder to accommodate. The community has largely moved away from this option, though it has never been definitively ruled out. The second proposal information is encoded on the event horizon, treats the horizon not as an empty geometric surface, but as a physical object with degrees of freedom. Every bit of information carried by infalling matter is recorded in the horizon state and subsequently released, highly scrambled, in the outgoing Hawking radiation. The radiation is not exactly thermal, it has tiny corrections, exponentially small in the black hole's entropy, that encode the initial state. In principle, an observer with complete knowledge of every outgoing photon from the beginning of evaporation to the end could reconstruct what fell in. In practice, this reconstruction is computationally intractable. The information is there, but extracting it would require a calculation of complexity that scales exponentially with the black hole's entropy, which, for a stellar mass black hole, is a number with roughly 10 to the 77 digits. The information is preserved in the technical sense of unitarity, while being operationally inaccessible in any sense a physical observer could exploit. This second proposal received mathematical support from a duality discovered in the late 1990s between certain theories of quantum gravity in anti-de Sitter space, a particular geometry of spacetime with a negative cosmological constant, and conformal field theories living on the boundary of that space. The duality is exact. Every gravitational process in the interior, including black hole formation and evaporation, has a precise dual description in terms of a quantum field theory on the boundary, and that boundary theory is manifestly unitary. If the duality holds, and there is substantial evidence that it does. At least in the specific geometries where it has been studied, then information cannot be lost in the interior theory either, regardless of what the semi-classical calculation appears to show. The information must escape in the radiation. The question of how it escapes and what the corrections to the thermal spectrum look like remains open. The third proposal, the firewall, emerged from pushing the second proposal's logic to its conclusion. If information is encoded in the early Hawking radiation, and if quantum mechanics requires that the early and late radiation be entangled with each other as unitarity demands, then the late radiation cannot also be entangled with the interior of the black hole. Quantum entanglement is monogamous. A particle that is maximally entangled with one system cannot be entangled with another. But general relativity says that an infalling observer crossing the event horizon should notice nothing special. The vacuum of spacetime near the horizon should look smooth, undisturbed, continuous with the exterior. That smoothness requires the vacuum fluctuations on either side of the horizon to be entangled with each other in a specific way. If the late radiation is entangled with the early radiation instead, that entanglement across the horizon is broken, and the broken entanglement corresponds, in quantum field theory on curved spacetime, to a divergent energy density at the horizon. A wall of high-energy radiation. Anything crossing the horizon would be incinerated rather than passing through smoothly. The firewall replaces the smooth horizon of general relativity with a physical surface of destruction. The firewall proposal does not obviously resolve the paradox, it relocates it. Instead of information being lost, the principle of equivalence, the cornerstone of general relativity, the statement that freely falling observers feel no local gravitational effects, fails at the horizon. Trading the violation of unitarity for the violation of equivalence does not obviously constitute progress. It clarifies the structure of the contradiction, and it has generated significant theoretical work on understanding how, precisely, the entanglement structure near the horizon should behave in a complete theory of quantum gravity. But it has not produced a resolution that commands consensus. The fourth proposal connects the information question to the interior structure question that the earlier acts have been building toward. If the interior of a black hole does not contain a singularity, if quantum gravity replaces the singularity with something else, something that has a well-defined quantum state, then the information does not need to escape through the Hawking radiation at all. It can be stored in the interior, in whatever structure quantum gravity places there, and released when the black hole completes its evaporation through whatever final state transition quantum gravity predicts at the Planck scale. The Planck star model from the previous act is one version of this. The information stored in the compressed core, released in the white hole explosion at the end. The fuzzball model, which will be examined next, is another. The information stored in the extended quantum structure that replaces the interior entirely, imprinted on the surface from the beginning. What these four proposals share is an agreement on the location of the problem. The singularity, or whatever exists where the singularity would be, is where general relativity fails. And it is also where the information question becomes impossible to answer within the framework of general relativity alone. The two problems are not separate difficulties requiring separate solutions. They are the same difficulty, approached from two different directions, one asking what happens to matter at the center, the other asking what happens to information at the end. Any theory that resolves one will, almost certainly, resolve the other. The question is what that theory looks like, and whether it treats the interior of a black hole as a place matter falls into and information escapes from, or as something whose very existence as a distinct region needs to be reconsidered from the beginning. There is a result in thermodynamics that most treatments of black holes mention briefly and then move past, but which, when you follow it carefully, leads somewhere genuinely strange. The result concerns entropy, the quantity that measures the number of distinct ways a physical system can be arranged internally while presenting the same external appearance. A glass of water has high entropy because the individual water molecules can be in an enormous number of different positions and velocities while the glass still looks and behaves like a glass of water. A crystal has low entropy because its molecules are locked into a specific arrangement, and deviating from that arrangement produces a different external appearance. Entropy is, in one precise sense, a measure of information, specifically the amount of information you would need to specify the complete microscopic state of a system, given knowledge of only its macroscopic properties. For most physical systems, entropy scales with volume. Double the volume of a gas while keeping the density the same, and the entropy doubles. There are twice as many molecules, each with its own position and velocity to specify. This is the expected behavior, the one that aligns with intuition about how information content should scale with size. Black holes do not behave this way. The entropy of a black hole, worked out through a combination of general relativity and quantum field theory, scales not with the volume enclosed by the event horizon, but with the surface area of the event horizon. Specifically, 1 bit of information per unit area equal to roughly 2.6 times 10 to the negative 66 square centimeters, the square of the Planck length, the smallest meaningful distance in physics. For a black hole with the mass of the Sun, whose event horizon has a radius of roughly 3 kilometers and a surface area of about 113 square kilometers, the total entropy is approximately 10 to the 77th bits. That is a number with 77 zeros, vastly larger than the entropy of the Sun as a normal star, and arrived at by counting not the volume of the black hole's interior, but the area of its surface. If the entropy, the information content of a black hole, is encoded on its two-dimensional surface, rather than distributed through its three-dimensional interior, what is the interior actually doing? The interior has volume. For a stellar mass black hole, that volume is roughly equal to a sphere 3 kilometers in radius. But all the information that could be contained within that volume, every possible configuration of matter and energy, is already fully specified by the state of the two-dimensional surface. The interior, in this accounting, is redundant. It carries no information that is not already present on the boundary. This is not a metaphor. It is a mathematical statement about where the degrees of freedom of the system actually reside. The implication, followed carefully, is that everything happening inside the black hole, every particle, every interaction, every process is completely determined by the state of the two-dimensional horizon. The three-dimensional interior is not a separate, additional piece of reality. It is a consequence of the boundary. The interior emerges from the surface the way a three-dimensional image emerges from a two-dimensional holographic film, not as an illusion, but as a physical reality that is fully encoded in a lower dimensional structure. The question that took several decades to clarify is whether this is specific to black holes or a general feature of spacetime. The answer came from a precise mathematical result connecting two theories that, on the surface, seem to have nothing to do with each other. One theory is a version of quantum gravity, a specific model of gravity in a spacetime with a particular geometry, called anti-de Sitter space, which has a constant negative curvature and a well-defined boundary at spatial infinity. The other theory is a quantum field theory, a description of particles and forces with no gravity living on the boundary of that space-time in one fewer dimension. The result is that these two theories are exactly equivalent. Every calculation in the gravitational theory in the interior has a precise dual in the quantum field theory on the boundary, and vice versa. Not approximately equivalent. Exactly, in the sense that every physical quantity computed in one theory has a corresponding quantity in the other, and the two agree. The significance of this equivalence for the information paradox is direct. The boundary quantum field theory is unitary. It conserves information exactly by the standard rules of quantum mechanics. If the two theories are exactly equivalent, then the gravitational theory in the interior must also conserve information, even when black holes form and evaporate. The information cannot be lost, because losing it in the interior would require losing it on the boundary, and the boundary theory does not permit that. The paradox, on this argument, is not a genuine contradiction but a signal that the semi-classical calculation of Hawking radiation is missing something, some correction, exponentially small in the black hole's entropy that encodes the initial state in the outgoing radiation. What the equivalence does not immediately tell us is what the interior of a black hole actually is in this picture. If the interior is encoded on the boundary, and the boundary is a quantum field theory with no gravity, then, in some sense, the interior space-time, including everything that falls through the event horizon, is a derived structure rather than a fundamental one. Space-time, on this view, is not the primary ingredient of reality. It emerges from something more fundamental, the entanglement structure of the boundary quantum field theory. Regions of space-time that are connected that can exchange signals correspond to regions of the boundary theory whose quantum states are strongly entangled. Regions that are disconnected correspond to regions with weak or absent entanglement. The geometry of space-time, the distances, the causal relationships, the very topology is a consequence of the pattern of quantum entanglement on a lower dimensional surface. There is a specific prediction this picture makes about black holes that connects back to the information paradox. When a black hole evaporates, its event horizon shrinks. The area of the horizon decreases. The entropy, the information capacity of the horizon, decreases. If the information that fell in is encoded on the horizon, then as the horizon shrinks, that information must be transferring somewhere into the outgoing Hawking radiation. The radiation must be carrying the information away in correlations between photons emitted at different times, correlations too subtle to detect in any finite sample of the radiation, but present in principle in the complete outgoing state. The black hole is not destroying information. It is slowly decoding the information written on its surface and releasing it into the radiation in an encoding so complex that it is operationally indistinguishable from random noise to any observer with access to less than roughly half the total emitted radiation. This picture has a consequence for what we mean by the interior of a black hole. If the interior is encoded on the horizon, and the horizon is shrinking as the black hole evaporates, then the interior is changing, not just getting smaller, but getting less well-defined. The degrees of freedom that were encoding the interior are being transferred to the radiation. In the final stages of evaporation, when the black hole has radiated away most of its mass, the interior, whatever structure was encoded there, has been almost entirely released into the outside universe. What remains is near Planck scale, a tiny remnant encoding the last bits of information, or a final explosion releasing them all at once, depending on which completion of the theory one assumes. The interior does not simply vanish. It is progressively transcribed into radiation, the way a document is transcribed into signals the original destroyed, the information preserved in a different form. Whether this description is literally correct, whether spacetime is genuinely emergent from entanglement on a boundary, depends on whether the mathematical equivalence established in the specific case of anti-de Sitter space extends to the actual universe, which does not have the geometry of anti-de Sitter space and has a positive rather than negative cosmological constant. That extension has not been established. It is an active area of research, and whether the holographic description applies to our cosmology to de Sitter space, the spacetime geometry appropriate to a universe with a positive cosmological constant and an accelerating expansion, is not currently known. The specific version of the duality that has been proven applies to a geometry our universe does not have. Whether the underlying principle that three-dimensional spacetime is encoded on a two-dimensional boundary is universal or specific to particular geometries is an open question. What is not open is the implication for black holes specifically. If the holographic encoding applies to black holes, and the evidence from the specific models where it has been studied suggests it does, then the interior of a black hole is not a separate region of spacetime that matter falls into and information disappears within. It is a structure encoded on the surface, emerging from the entanglement of degrees of freedom that are, in some sense, accessible from outside. The event horizon is not a barrier that information cannot cross. It is the surface on which all the information about the interior is written. And what that surface contains, the complete quantum state of everything that has ever fallen in, is, in principle, readable from outside if you know how to decode it. Whether anyone ever will is a separate question. The information is there. The question of what it describes what the interior of a black hole actually looks like from the perspective of the boundary theory is the question the next proposal addresses most directly. The Schwarzschild solution to Einstein's field equations does not describe just a black hole. It describes a maximally extended spacetime, a complete geometric structure that contains four distinct regions, connected in ways that the standard presentation of black holes usually omits. Region 1 is the exterior, the universe we inhabit, where the black hole's gravity is felt, but its interior is inaccessible. Region 2 is the black hole interior, the region bounded by the future event horizon, inside which all causal paths lead toward the singularity. Region 3 is a second exterior, a space-time region with the same geometry as Region 1, connected to it through the wormhole throat, but causally disconnected from it. No signal from Region 1 can reach Region 3, and no signal from Region 3 can reach Region 1. Region 4 is the white hole interior, the time reverse of the black hole, a region from which signals can escape into either exterior, but into which nothing from outside can enter. This four-region structure is the complete Schwarzschild spacetime. The black hole we normally discuss, the object formed by stellar collapse, surrounded by an accretion disk, detectable through its gravitational effects, corresponds to a portion of this geometry. The other regions exist in the mathematics of the eternal Schwarzschild solution, but their physical relevance depends on whether they are realized in any actual spacetime produced by gravitational collapse. For a black hole formed from the collapse of a star, the regions corresponding to the white hole interior and the second exterior are generally not present. The collapse geometry does not produce them. They appear in the eternal solution, a black hole that has existed forever and will exist forever, but not in the physical solution describing a black hole with a finite formation time. What quantum gravity does to this picture is the central question. In classical general relativity, the singularity in Region 2 is a genuine endpoint matter that crosses the event horizon, reaches the singularity in finite proper time and ceases to have a causal future. If quantum gravity replaces the singularity with something else, some structure at Planck density that does not terminate the causal future of infalling matter, then the geometry past the singularity becomes physically relevant. And what lies past the singularity, in the maximally extended solution, is region 3, a second exterior spacetime. Whether that region is our universe viewed from a different direction, a causally distinct region with different boundary conditions, or something that requires new concepts to describe, is not determined by the classical geometry alone. It depends on what the quantum bounce or whatever replaces the singularity actually produces. The connection between the two exterior regions, the wormhole throat, is where the physics becomes most precisely stated and most precisely uncertain simultaneously. In the eternal Schwarzschild solution, the throat connecting region 1 and region 3 exists but is not traversable. Any attempt to pass through it, any signal or particle trying to travel from one exterior to the other, arrives after the throat has collapsed. The geometry is dynamic. The throat opens, reaches a maximum radius, and pinches off, all in a finite time that is shorter than the time required for light to cross from one side to the other. The wormhole exists but cannot be used. Making it traversable requires matter with properties that violate the energy conditions of classical general relativity, specifically matter with negative energy density, which would counteract the gravitational tendency of the throat to collapse. Quantum field theory does permit states with locally negative energy density. The Casimir effect between conducting plates is a laboratory measurable example, but whether such states can be maintained stably at the scales, and energies required to hold a macroscopic wormhole open is not currently known. The energy required scales with the size of the wormhole. A traversable wormhole large enough for a person to pass through would require negative energy in quantities that appear to exceed what any realistic quantum system could provide. There is a separate proposal not about traversable wormholes as passages, but about wormholes as the structural basis of entanglement that connects the geometry question to the information question from the previous act. The proposal notes a formal resemblance between two structures in physics. The first is the Einstein-Rosen bridge, the wormhole connecting the two exterior regions in the maximally extended Schwarzschild solution. The second is quantum entanglement between two separated systems, the EPR correlation, named for Einstein, Podolsky, and Rosen, the same Einstein who co-authored the bridge paper. The resemblance is not superficial. In the specific models where the holographic duality applies, a pair of entangled black holes, two black holes whose quantum states are maximally entangled with each other, has been shown to correspond to a single spacetime in which the two black holes are connected by a wormhole throat. The entanglement and the geometric connection are the same thing, described in two different languages, quantum information theory and general relativity. The implication runs in both directions. If entanglement between two systems corresponds to a geometric connection between them, then increasing the entanglement corresponds to making the connection more robust, the wormhole throat becoming larger or more stable. Decreasing the entanglement corresponds to the throat shrinking. At zero entanglement, the two regions are geometrically disconnected, no wormhole, no causal path between them. Space-time connectivity, on this picture, is a consequence of entanglement. Two regions of space are connected, can exchange signals, share a geometry because the quantum systems describing them are entangled. The geometry of space is not fundamental. It emerges from the entanglement structure of the underlying quantum theory. This has a direct consequence for the interior of a black hole. The interior region 2, the region inside the event horizon, is, in the holographic description, encoded on the event horizon. But it is also connected through the wormhole geometry to another region, either a second exterior or, in the case of Hawking evaporation, to the early radiation that has already been emitted. As the black hole evaporates and the early radiation accumulates, the entanglement between the remaining black hole and the early radiation grows. In the geometric language, this means the wormhole connecting the interior to the radiation system grows. The geometric connection between what is inside and what has been emitted becomes more substantial. The interior is not isolated from the exterior radiation. It is geometrically connected to it through an entanglement wormhole structure that becomes more elaborated as evaporation proceeds. Information about the interior state is accessible, in principle, through the radiation, not because it has escaped through the event horizon, but because the horizon is connected to the radiation through the same geometric structure that produces the interior. Whether this picture is literally correct, whether the wormhole connection between black hole interior and external radiation is a real geometric feature of spacetime or a mathematical artifact of the duality is not settled. What is clear is that it provides a consistent resolution of the information paradox without requiring any violation of either quantum mechanics or general relativity in their respective domains. The information is not lost. The interior is not destroyed. The event horizon is not a barrier that severs all connection between inside and outside. It is a surface whose geometry is entangled with the geometry of everything that has been emitted, and the full state of the system interior plus radiation remains unitary throughout the evaporation. The interior and the exterior are the same system, described from different perspectives, the same way that the two sides of a holographic duality describe the same physics in different languages. There is one version of the other side question that this geometric picture addresses most directly. If the interior of a black hole is connected through entanglement wormhole structure to the external radiation, and if that radiation, after sufficient evaporation, has been collected by some observer outside, then that observer, in principle, has access to information about the interior. Not by looking through the event horizon, which remains causally impenetrable, but by decoding the correlations in the radiation, which are geometrically connected to the interior through the wormhole structure. What is on the other side of the black hole, on this picture, is not a separate universe or a different region of space-time unreachable by any means. It is encoded in the radiation that the black hole has been emitting since it formed present in the correlations between photons, accessible to anyone who has collected enough of the outgoing radiation and has the computational resources to decode it. The other side is here, distributed through the radiation field, waiting to be read. Whether reading it constitutes knowing what is inside, whether the decoded information gives you the same knowledge that an observer who actually crossed the horizon would have, is a question the current theory leaves, precisely and perhaps deliberately, unanswered. A gamma-ray burst releases, in a matter of seconds, more energy than the sun will produce across its entire 10 billion-year lifetime. That sentence requires a moment. The sun outputs roughly 3.8 times 10 to the 26th watts, continuously enough energy per second to power all of human civilization for the next several 100,000 years. A gamma-ray burst, in its peak emission phase, can match or exceed that total lifetime output in under a minute. The energy is not spread uniformly in all directions. It is collimated, focused into two narrow jets, each spanning only a few degrees of solid angle, pointed in opposite directions along the rotation axis of whatever produced them. Within those jets, the energy density is so extreme that the photons themselves begin interacting with each other, gamma rays colliding to produce electron-positron pairs, which annihilate back into gamma rays, creating a cascade of particle-antiparticle creation and destruction that propagates outward at close to the speed of light. Long-duration bursts, those lasting more than roughly 2 seconds, originate from the core collapse of massive stars. When a star with a mass exceeding roughly 25 solar masses exhausts its nuclear fuel, the iron core that has been accumulating at its center, the end product of successive fusion stages that burned hydrogen into helium, helium into carbon, carbon into neon and oxygen and silicon, and finally iron, each stage producing less energy than the last, collapses in under a second. The collapse releases gravitational potential energy equivalent to roughly 10 to the 46 joules, comparable to what the sun will radiate across its entire life in the form of neutrinos in approximately 10 seconds. A fraction of that energy couples to the stellar envelope and drives an explosion outward. The collimated jets, powered by accretion onto the newly formed compact object at the center, punch through the collapsing stellar material and emerge as the gamma ray burst. Short-duration bursts under 2 seconds come from a different process. 2 neutron stars in a binary system, having lost orbital energy to gravitational wave emission over millions of years, spiral together and merge. The merger, which takes milliseconds from first contact to completion, produces a remnant of roughly 2 to 3 solar masses, either a heavy neutron star or a black hole, depending on the mass and spin, surrounded by a disk of neutron-rich debris. The disk accretes rapidly, powering jets that produce the burst. The merger also produces gravitational waves, a chirp signal lasting fractions of a second, and, through the rapid neutron capture process in the debris disk, synthesizes heavy elements, gold, platinum, uranium, and the majority of elements heavier than iron that exist in the universe. Every gold atom on Earth was produced in a neutron star merger. Now, consider what happens when the jet from one of these events intersects with a black hole. Not a conceptual intersection, a physical one, where photons with individual energies exceeding 10 to the 15 electron volts travel through the curved spacetime in the immediate vicinity of an event horizon. At those energies, each photon carries more energy than a flying mosquito, which sounds trivial until you note that a photon is massless and a mosquito weighs roughly 2 milligrams, and the comparison is between kinetic energy and electromagnetic energy at the quantum scale. The photon sphere, around a black hole, the radius at which circular photon orbits are possible, sits at 1.5 times the Schwarzschild radius for a non-rotating black hole and closer for a maximally rotating one. Photons from a GRB jet passing through this region do not simply travel in straight lines. They follow null geodesics, the straightest possible paths through curved spacetime, which near the photon sphere can include orbits, partial orbits, and paths that loop around the black hole multiple times before continuing outward. The observable consequence of this is a sequence of delayed echo images. An observer positioned away from the black hole, watching the GRB jet illuminate the region around the horizon, would see not a single flash, but a series of them, each successive image corresponding to photons that completed an additional half-orbit around the black hole before escaping. The time delay between images increases exponentially with the number of orbits. The first echo arrives after a delay set by the orbital period at the photon sphere, the second after roughly twice that, the third after roughly 4 times that, and so on. The images become exponentially fainter with each additional orbit, because each successive orbit deflects a smaller, solid angle of the incoming beam. But in principle, an infinite series of echo images exists, each one fainter and more delayed than the last, converging on the photon sphere like the terms of a convergent series. For photons that actually cross the event horizon, the portion of the jet directed precisely enough at the black hole's center to enter the process is different. Photons carry energy, and energy is equivalent to mass. A black hole that absorbs photons from a GRB gains mass at a rate proportional to the energy flux crossing its horizon. For a stellar mass black hole of 10 solar masses with a Schwarzschild radius of 30 kilometers, the cross-sectional area available to intercept the jet is roughly 3,000 square kilometers. A GRB jet with a total energy of 10 to the 44 joules, collimated into a beam a few degrees wide, delivers energy to that cross-section at a rate that increases the black hole's mass by a fraction of a percent at most. The change is real but small. The Schwarzschild radius increases proportionally with mass. Add 1% to the mass, and the event horizon expands by 1%. The geometry outside the horizon adjusts accordingly, imperceptibly. More physically significant is what happens to the photons near the event horizon before they cross it. At energies above roughly 1 mega-electron volt, well below the energies of GRB photons, which reach 10 to the 15 electron volts or higher, photons can spontaneously produce electron-positron pairs when they interact with other photons or with strong electromagnetic fields. The environment near an active black hole's event horizon, where accretion disk photons and magnetic fields with strengths of millions of Gauss coexist, provides both conditions simultaneously. GRB photons entering this environment would drive prolific pair production, each high-energy photon creating multiple electron-positron pairs, each of which can annihilate or interact further, producing a cascade that deposits enormous energy into the region just outside the horizon. The result is a sudden increase in the opacity and energy density of the plasma surrounding the black hole. The accretion flow becomes temporarily more luminous, the magnetic field is amplified by the additional current, and the structure of the innermost disk is disrupted. There is a gravitational wave component to consider as well. The GRB jet carries not just electromagnetic energy, but momentum, and when that momentum is deposited asymmetrically into the black hole, it contributes a small kick to the black hole's linear momentum and a change to its spin. The spin change, though tiny for a single GRB, is not zero. A black hole's spin, characterized by a dimensionless parameter between 0 and 1, where 1 represents maximal rotation, determines the location of the innermost stable circular orbit, which in turn determines the efficiency of accretion. A maximally spinning black hole converts up to 42% of infalling mass energy into radiation, as noted earlier. A non-rotating one converts only about 6%. Anything that changes a black hole's spin changes how efficiently it radiates. For all subsequent accretion, a small perturbation with potentially long-lasting consequences for the black hole's subsequent evolution. The most sensitive probe of what happens when high-energy photons interact with strong spacetime curvature is not the direct observation of a GRB hitting a black hole. No such event has been confirmed yet, but the green 1970s 74R propagation of GRB photons across cosmological distance. If spacetime has a minimum length scale, a granularity at the Planck scale, as some quantum gravity theories propose, then photons of different energies would propagate at very slightly different speeds, the higher energy photons being slowed slightly more by their interaction with the discrete structure of spacetime. Over cosmological distances, this tiny energy-dependent speed difference would accumulate into a measurable time delay between the arrival of high-energy and low-energy photons from the same burst. GRBs, producing photons across an enormous energy range simultaneously, are the ideal source for searching for this effect. The delay predicted by Planck scale granularity for a burst at redshift 1 roughly 8 billion light-years away would be on the order of seconds at most, for photons differing in energy by a factor of 10 to the 10. Such delays have been searched for, and the results have constrained the energy scale of any Lorentz violation to be at least 10 to the 19th giga-electron volts at or above the Planck energy. Spacetime appears smoothed down to scales we cannot probe with any other method. The GRB photons, after traveling billions of light-years through the most curved and energetic environments the universe produces, arrive with timing consistent with a perfectly smooth spacetime, which is itself a result worth holding for a moment. The universe's most energetic photons, produced by its most violent events, propagating through its deepest gravitational fields, testing the structure of space-time at every scale accessible to observation, and finding it smooth, consistent, continuous. General relativity, written down without the benefit of any of these observations, predicts exactly this behavior. The smoothness is not surprising in hindsight. It was never guaranteed in advance. And the fact that it holds that the same geometry describing the orbit of the moon also describes the propagation of the universe's most energetic photons through the deepest gravitational wells we can find is the most precise confirmation that the theory we have been using throughout this entire series of acts is, at every scale we can reach, correct. What it fails to describe remains beyond the horizon. But what it succeeds in describing is, by any reasonable measure, everything else. Black holes have a temperature. Not metaphorically, physically, measurably, in the sense that they emit thermal radiation at a specific temperature determined by their mass. The relationship is inverse. The more massive the black hole, the lower its temperature. A black hole with the mass of the Sun radiates at approximately 60 billionths of a Kelvin, a temperature so far below the cosmic microwave background's 2.7 Kelvin that the black hole is, effectively, absorbing more radiation from the universe than it emits. It cannot evaporate under current cosmic conditions because the universe itself is hotter than it is. For a black hole to begin losing mass through its own radiation, the universe must first cool below the black hole's temperature, which, for a solar mass black hole, means waiting until the universe is roughly 10 to the 19th times older than it currently is. The temperature formula scales with the inverse of mass. Halve the mass, and the temperature doubles. Halve it again, and the temperature doubles again. As a black hole evaporates and loses mass, it gets hotter, which causes it to radiate faster, which causes it to lose mass faster, which makes it hotter still. The process is self-accelerating in its final stages. A black hole that has been evaporating for 10 to the 67th years, losing mass at an imperceptibly slow rate, will in its final second emit as much energy as it has emitted across its entire prior existence. The last moment is not a quiet fade. It is, proportionally, the most violent event in the black hole's entire history. For a black hole with the initial mass of the Sun, the total evaporation time is approximately 2 times 10 to the 67th years. The current age of the universe is approximately 1.4 times 10 to the 10 years, 14 billion years. 2 times 10 to the 67th years is roughly 10 to the 57 times longer than the current age of the universe. If the entire history of the universe to date were compressed into a single second, the evaporation timescale for a solar mass black hole would be approximately 3 times 10 to the 49th seconds, a number with 49 zeros, in a unit of time that is itself already a compression of 14 billion years. These numbers resist intuition. What they convey is that the final evaporation of any black hole formed from stellar collapse is an event of the extremely distant future, a future so remote that every star currently burning in the universe will have exhausted its fuel and cooled to darkness roughly 10 to the 47 times before the first solar mass black hole completes its evaporation. Supermassive black holes evaporate on correspondingly longer timescales. Evaporation time scales with the cube of the mass double the mass, and the evaporation time increases by a factor of 8. For a black hole of 4 million solar masses, the mass of the Milky Way's central black hole, the evaporation time is roughly 10 to the 83 years. For Ton 618, at 66 billion solar masses, the evaporation time exceeds 10 to the 99 years. By the time TON 618 completes its evaporation, the universe will have passed through cosmological epochs that have no names, yet epochs so remote from the present that the physical processes characterizing them have not been fully worked out. The protons that make up ordinary matter may have decayed. The remaining black holes may be the only gravitationally bound structures left in an otherwise uniform sea of cold radiation. The thought experiment of all black holes evaporating simultaneously is not physically realizable. Black holes of different masses evaporate on timescales that differ by factors of 10 to the 89 or more. There is no mechanism known to physics, no force, no field, no cosmic event that could synchronize these processes. The universe does not have a timer. Each black hole completes its evaporation independently, at a time set by its initial mass and the rate at which it has accreted additional material since formation. The last black hole to evaporate will do so alone, in a universe that has been dark for an incomprehensibly long time. The simultaneous scenario is useful not as a physical prediction, but as a way of making the cumulative energy budget of black hole evaporation concrete, asking what the universe's total energy output from this process would be if it were somehow compressed into an instant. That total energy is set by the initial masses of all black holes that have ever formed. Every unit of mass that crosses an event horizon will eventually be returned to the universe as Hawking radiation thermal photons, gravitons, neutrinos, and, in the final Planck scale burst, potentially heavier particles as the temperature exceeds the production thresholds for all known particle species. The total energy returned is exactly equal to the total mass energy that fell in, less any mass energy that was itself radiated away by the accretion process before crossing the horizon. Mass energy is conserved. The black hole does not destroy energy. It stores it in a form that is returned to the universe on timescales that make geological time seem instantaneous by comparison. What the final burst of each individual black hole looks like is constrained by the physics of the Planck scale. When a black hole's mass reaches the Planck mass approximately 22 micrograms, roughly the mass of a human cell, its temperature reaches the Planck temperature, approximately 1.4 times 10 to the 32 Kelvin. At that temperature, the thermal wavelength of the emitted radiation is comparable to the Schwarzschild radius of the black hole, and the semi-classical approximation underlying the Hawking calculation breaks down. The final emission, whatever it is, cannot be described by the standard Hawking formula. It requires a complete theory of quantum gravity, which does not currently exist in a form that produces unambiguous predictions for this regime. What is generally expected, though not derived from any complete calculation, is a final burst of hard radiation, carrying away the last Planck mass of energy in a time on the order of the Planck time, approximately 5 times 10 to the negative 44 seconds. The burst would be isotropic, intense, and extremely brief. It would produce particles across the full spectrum of standard model species, since at Planck temperature every known particle can be thermally produced. For a primordial black hole, a black hole formed not from stellar collapse, but from density fluctuations in the early universe, possibly in the first fraction of a second after the Big Bang, the evaporation timescale depends on the initial mass. Primordial black holes, formed with masses of roughly 5 times 10 to the 11 kilograms, about the mass of a large mountain, would complete their evaporation at approximately the current age of the universe. Their final bursts would be occurring now, somewhere in the universe, producing gamma-ray signals of a specific character, a thermal spectrum with a peak energy set by the Planck temperature, isotropic in the rest frame of the evaporating black hole, with a duration of fractions of a second. Whether such bursts have been observed is not established. The gamma-ray sky contains numerous transient sources, and distinguishing a primordial black hole evaporation from other transient phenomena requires identifying the specific spectral and temporal signature of the Planck temperature burst. That signature has been searched for. No confirmed detection has been reported. The absence of detections places constraints on the abundance of primordial black holes in the relevant mass range, constraints that are consistent with primordial black holes making up at most a small fraction of the dark matter. There is a version of the simultaneous evaporation scenario that is physically motivated, though it requires speculative physics. If the Planck star model is correct, if black holes, when they reach Planck mass, transition into white holes and release their information in a final burst, then the distribution of these bursts across cosmic time is set by the distribution of black hole formation times and masses. In the very far future, as the last stellar mass black holes approach the end of their evaporation, there would be a period during which the rate of Planck star explosions was at its maximum, not simultaneous, but concentrated in a cosmic era that, from the perspective of the long history of the universe, would appear as a relatively brief epoch of final releases. Whether that epoch would be observable, whether any structure capable of observation would persist to witness it, depends on physics that has not been established. What the energy budget of black hole evaporation clarifies is the thermodynamic trajectory of the universe. The universe began in a state of low entropy, the hot, dense, nearly uniform Big Bang, and has been increasing in entropy ever since, as stars burn, matter disperses, and structure forms and dissolves. Black holes represent the highest entropy objects of a given mass that can exist. Their entropy, proportional to their surface area, exceeds that of any other configuration of equivalent mass energy. As matter falls into black holes throughout cosmic history, the universe's total entropy increases. As black holes evaporate, returning that mass energy to thermal radiation, the entropy of the radiation is at least as large as the entropy of the black holes that produced it. The process is irreversible, as thermodynamics requires. The universe's entropy increases monotonically. The final state, after all black holes have evaporated, is a universe of cold, diffuse thermal radiation, the highest entropy configuration available to the matter energy content of the observable universe. The Hawking process is not a reset. It is the universe completing the thermodynamic trajectory it began at the Big Bang and arriving, after an incomprehensible duration, at the state that thermodynamics has been pointing toward all along. Jupiter contains 1.9 times 10 to the 27th kilograms of mass. To put that in terms of something meaningful, Jupiter is more massive than all the other planets in the solar system combined, by a factor of roughly 2.5. It contains enough hydrogen that if you added about 80 times more, the pressure at its core would ignite nuclear fusion and it would become a star. It did not get that extra mass, so it sits at the upper boundary of what a gas planet can be, the largest possible version of the thing it is, without crossing into the category above. Its magnetic field is the strongest of any planet in the solar system, roughly 20,000 times stronger than Earth's. Its Great Red Spot, a storm that has persisted for at least 350 years, is wide enough to contain two Earths side by side. By every planetary measure, Jupiter is extreme. None of that matters near a black hole. What matters, as established earlier in this series, is the tidal gradient, the difference in gravitational pull across the diameter of an object. For Jupiter, with a mean radius of roughly 71,000 kilometers, that diameter is about 142,000 kilometers. The tidal force acting across that diameter depends on the mass of the black hole and the distance from it. There is a specific distance, the Roche limit, inside which the tidal gradient exceeds Jupiter's own self-gravity, and the planet can no longer hold itself together. For a stellar mass black hole of 10 solar masses about 30 kilometers across, Jupiter's Roche limit sits at roughly 1 million kilometers from the black hole's center. 1 million kilometers is about 2.5 times the distance from Earth to the Moon. At that distance, Jupiter begins to structurally fail, not because the black hole has touched it, but because the geometry of spacetime across Jupiter's diameter has become sufficiently unequal that Jupiter's gravity can no longer keep itself in a sphere. The sequence of events inside the Roche limit proceeds in a specific order. The gas on the side of Jupiter facing the black hole accelerates toward it faster than the gas on the far side. Jupiter elongates along the line, connecting it to the black hole, stretching in that direction while compressing perpendicular to it, the same deformation that tidal forces produce in any extended object. Jupiter's atmosphere, which extends outward in all directions at normal conditions, begins streaming away from the side closest to the black hole. The departure is not violent initially. It resembles, in structure, if not in scale, the way a star loses mass to a companion in a binary system, a slow overflow of material across the gravitational boundary between the two objects. But the rate accelerates as Jupiter loses mass and its self-gravity weakens, which reduces the Roche limit, which causes more mass to overflow, which weakens self-gravity further. The process is self-amplifying, and the timescale compresses from millions of years at the outer limit to hours as Jupiter approaches structural failure. The departing gas does not fall straight into the black hole. It retains angular momentum from Jupiter's orbital motion and its own rotation, roughly 10 hours per revolution, and this momentum causes the infalling material to curve into an orbit around the black hole rather than plunging directly in. The material forms an accretion disk, a flattened, rotating structure extending from close to the black hole's event horizon outward to roughly the distance where Jupiter was when disruption began. Within the disk, successive layers of gas collide with each other, the inner material moving faster, the outer moving slower, and the friction between them converts orbital kinetic energy into heat. The temperature of the disk rises steeply toward the innermost edge, reaching millions of Kelvin near the innermost stable circular orbit, the closest radius at which matter can stably orbit without falling in. At those temperatures, the gas radiates primarily in X-rays, not the warm infrared of a planet, not the visible light of a star, but high-energy photons capable of ionizing atoms at distances of millions of kilometers. The brightness of this accretion event is set by the rate at which mass falls through the disk. Jupiter's total mass, accreted over hours to days, represents an enormous energy source. At the Eddington efficiency for a 10 solar mass black hole, roughly 10% of infalling mass energy converted to radiation, Jupiter's destruction would release approximately 1.7 times 10 to the 44 joules. The Sun's total lifetime output is approximately 1.2 times 10 to the 44 joules. Jupiter falling into a stellar mass black hole would, across the duration of the disruption event, release energy comparable to the Sun's entire lifetime, output compressed into hours to days rather than 10 billion years. The luminosity during peak accretion would exceed the Sun's output by many orders of magnitude. From Earth, at 778 million kilometers, roughly 5 astronomical units from the event, this source would be bright enough to see in daylight if Earth's atmosphere and ozone layer survived long enough to provide a stable viewing platform. They would not. The X-ray flux from the accretion disk, at Earth's distance from the disruption event, would be sufficient to destroy the ozone layer within hours. Without the ozone layer, ultraviolet radiation from both the accretion disk and the Sun would reach the surface at lethal intensities. The higher energy X-rays would penetrate the atmosphere and ionize molecules at lower altitudes, disrupting atmospheric chemistry on global scales. The magnetosphere, Earth's primary shield against charged particle radiation, would be overwhelmed by the relativistic particle jets that form along the black hole's magnetic axis during active accretion, if those jets happen to be directed toward Earth. The timing of all of this, relative to Earth's survival, depends on the geometry of the encounter and the orientation of the jet's parameters that would be set by the specifics of how the black hole entered the solar system, how Jupiter's disruption proceeded. What is not geometry dependent is the general conclusion. The radiation environment produced by Jupiter's disruption would be lethal to surface life on Earth, and probably to subsurface life as well, on timescales of days to months. The effect on the solar system's orbital architecture begins even before Jupiter reaches the Roche limit. Jupiter's gravitational influence on the inner solar system is substantial and continuous. It is the dominant perturber of the asteroid belt. Its gravitational resonances prevent the asteroids between Mars and Jupiter from ever accreting into a planet, and they periodically inject asteroids onto Earth-crossing orbits. It also deflects comets from the outer solar system, some inward toward potential Earth impact, and others outward, away from the inner system. The net effect of Jupiter's presence on the impact rate at Earth is a subject of ongoing research, but the directional effect is clear. Remove Jupiter, and the dynamics of small bodies in the solar system changes substantially. The introduction of a 10 solar mass black hole at Jupiter's location would not simply remove Jupiter's gravitational influence, it would replace it with a gravitational source roughly 10 times stronger in the same location, pulling all nearby material toward it, rather than redistributing it through resonances and scattering. The Kuiper belt and the scattered disk would be strongly perturbed. Comets, currently in stable orbits in the outer solar system, would be deflected inward, producing an impact surge at Earth that would persist for millions of years as successive waves of cometary material arrived. The black hole's own effect on Earth's orbit is gravitational. A 10 solar mass object at 5 astronomical units exerts a gravitational force on Earth comparable to Jupiter's current influence, stronger, actually, since 10 solar masses exceeds Jupiter's mass by roughly a factor of 10,000. Earth's orbit, currently nearly circular, would be perturbed into a more elliptical path over timescales of thousands to millions of years depending on the specifics of the black hole's trajectory through the solar system. Whether the perturbation ultimately ejects Earth from the solar system, sends it inward toward the Sun and the black hole, or settles into a new stable configuration, is a three-body problem analytically intractable and sensitive to initial conditions. What is tractable is the conclusion that Earth's current orbit, calibrated over billions of years of planetary evolution into a nearly circular path at the right distance for liquid water, would not survive the introduction of a 10 solar mass perturber at Jupiter's current position. For a supermassive black hole, one with millions of solar masses, where the event horizon spans millions of kilometers, the Roche limit for Jupiter sits much farther out, and Jupiter could cross the event horizon intact. From outside, the crossing would be invisible in the conventional sense. Jupiter's image, as seen by a distant observer, would redshift and dim as it approached the horizon, gravitational redshift stretching each photon to longer wavelengths, time dilation stretching the interval between successive photons. Jupiter would appear to slow, freeze, and fade its image, persisting asymptotically, dimming below any detectable threshold over a finite time, but never reaching complete darkness in finite external time. From Jupiter's perspective, if such a thing were meaningful, the crossing would be unremarkable at the moment of crossing. No local signal, no barrier, just the continuation of free fall into a region from which the external universe is no longer accessible. What happens subsequently, as Jupiter falls deeper and the tidal gradient grows, follows the same sequence as the stellar mass case, just on a larger scale and a longer time scale, the fatal tidal forces arriving later, deeper, as the curvature steepens toward whatever exists at the center. Whether Jupiter, compressed and ionized and stripped of every structure that made it a planet, contributes anything distinct to what already exists inside, or whether the black hole simply absorbs 1.9 times 10 to the 27th kilograms of additional mass with complete indifference to its origin, is a question the interior physics must answer. From outside, the answer is the same either way. The event horizon expands by an amount proportional to the added mass, and the exterior geometry adjusts accordingly. Nothing about the outside changes in any way that distinguishes Jupiter from an equivalent mass of hydrogen gas. In April of 2019, a collaboration of radio telescopes distributed across 6 continents, synchronized to within a fraction of a picosecond using atomic clocks, collecting data that required the equivalent of 5 petabytes of hard drives to store, produced a single image. It showed an asymmetric ring of orange-yellow light surrounding a dark central region. The ring was not uniform. One side was brighter than the other. The dark center was not featureless. It had a specific shape, slightly off-center from the ring's geometric center. The object producing the image was a black hole, 6.5 billion times the mass of the Sun, located 55 million light-years away in the constellation Virgo. Every feature of the image, the ring's diameter, its brightness asymmetry, the shape of the shadow, matched the predictions of general relativity to within the measurement uncertainties. Not approximately, within the error bars. What you are looking at in that image is not the black hole itself. Nothing from inside the event horizon can reach the detector. What you are looking at is the photon ring, a concentration of light at the radius where photons orbit the black hole rather than escape from it or fall into it. That radius, called the photon sphere for a non-rotating black hole, and the photon shell for a rotating one, is where the competition between gravity pulling inward and the photon's tendency to travel in a straight line through curved spacetime is precisely balanced. A photon At exactly the photon sphere radius travels in a circular orbit, not because it is trapped, but because the geodesic it follows, the straightest possible path through the curved spacetime at that location, happens to be circular. Photons slightly outside this radius follow paths that curve toward the black hole but eventually escape. Photons slightly inside follow paths that curve inward and cross the event horizon. At exactly the photon sphere, the photon orbits indefinitely, or would, in a perfectly symmetric spacetime without perturbations. In reality, the photon sphere is unstable. Any small perturbation, a slightly off-center trajectory, an interaction with a photon from the accretion disk will send a photon either outward toward escape or inward toward the horizon. But photons that pass close to the photon sphere without quite reaching it can loop around the black hole 1, 2, 3, or more times before finally escaping. Each additional loop delays the photon's arrival at the detector. Each additional loop brings the photon's path closer to the photon sphere, and therefore takes it through regions of higher spacetime curvature, gathering more information about the geometry near the horizon. What the detector receives is a superposition of all these delayed, multiply-looped images, each one a slightly different view of the same emitting region, stacked into the structure of the ring. The brightness asymmetry in the image encodes the black hole's spin. A rotating black hole drags the space-time around it, a phenomenon called frame dragging, or the Lentz-Thirring effect. Gas in the accretion disk orbiting on the side, rotating toward the observer, has its emitted photons, blue-shifted, compressed to shorter wavelengths, higher energies, greater brightness by the combination of orbital motion and frame dragging. Gas on the opposite side has its photons redshifted, stretched to longer wavelengths, lower energies, dimmer appearance. The result is that one side of the photon ring appears brighter than the other. The degree of asymmetry depends on the black hole's spin parameter and the inclination of its rotation axis relative to the line of sight. From the measured asymmetry in the M87 image, the black hole's spin can be constrained, though not yet with high precision, because the accretion disk geometry introduces uncertainties. Future observations with higher resolution will tighten those constraints. The dark central region, the black hole shadow, has a specific predicted size relative to the photon ring. For a Schwarzschild black hole, non-rotating, the shadow diameter is exactly 2 times the square root of 27 times the Schwarzschild radius. For a maximally rotating Kerr black hole, the shadow is slightly smaller and asymmetric. Measuring the shadow size and shape tests whether the object at the center behaves as general relativity's black hole solutions predict. For M87, the measured shadow size corresponds to a mass of 6.5 billion solar masses, consistent with prior estimates from stellar dynamics in the galaxy's core. The shadow is not, strictly speaking, the event horizon. It is the projection of the photon capture cross-section onto the sky, the region of apparent darkness, produced by the fact that all photons whose trajectories intersect the event horizon are removed from the observable flue. It is larger than the event horizon by a factor of approximately 2.6 for a non-rotating black hole. The image of Sagittarius A star, released in 2022, presented a different technical challenge. Sagittarius A star is 26,000 light-years away, roughly 2,000 times closer than M87. Its mass is 4 million solar masses, roughly 1,600 times less than M87. These two factors, closer distance and smaller mass, combine to make its apparent angular size on the sky comparable to M87's, which is why both were imaging targets for the same instrument. But Sagittarius A star's smaller mass means the orbital timescale near the photon sphere is much shorter material orbits in minutes rather than days. This means the accretion disk structure changes on timescales comparable to the observing period, making the image construction more complex. The final image required averaging over many realizations of the accretion flow to produce a stable picture rather than treating the source as static. The result nonetheless showed the same photon ring structure, a bright ring surrounding a dark shadow, consistent with general relativity's predictions for a 4 million solar mass Kerr black hole. What the photon ring can tell us about the interior of the black hole is a question currently at the boundary of theoretical understanding. In the standard picture, a black hole described by the Kerr metric of general relativity, the photon ring structure is determined entirely by the mass and spin of the black hole. Any two objects with the same mass and spin produce identical photon rings, regardless of what their interiors contain. This is the no-hair theorem of black hole physics. A black hole is completely characterized by three external parameters: mass, spin, and charge, and its exterior geometry carries no information about how it formed or what its interior structure is. If this theorem is exact, and it is exact within classical general relativity, then the photon ring image cannot distinguish a classical Kerr black hole from any other object of the same mass and spin that is compact enough to state, have a photon sphere. A fuzzball, as string theory proposes the interior to be an extended quantum object rather than an empty spacetime with a singularity, would produce the same photon ring as a classical black hole if its exterior geometry matches Kerr to sufficient precision. But there are corrections. Quantum effects near the horizon are expected to produce deviations from the classical Kerr geometry deviations that grow near the horizon and would be most visible in the highest order subrings of the photon ring, the ones produced by photons that have looped many times and therefore sampled the geometry nearest the horizon most intensely. Each successive subring is exponentially fainter than the previous. The ratio between successive subring fluxes is roughly 1 to 500, making direct observation of even the first subring beyond current capabilities. But next-generation instruments, with substantially higher angular resolution achieved by extending the baseline to space, could, in principle, detect these subrings. A deviation in the subring spacing or brightness ratio from the classical Kerr prediction would be the first observational signature of quantum corrections to black hole geometry. That measurement, if it is ever made, would represent the first direct test of quantum gravity. Not indirect evidence. Not a theoretical consistency check. A measurement of the photon ring that does not match the prediction of classical general relativity would mean that something in the near horizon region is different from what the theory predicts, something that requires quantum gravity to explain. It would not tell us what the interior is. The no-hair structure of the exterior geometry is deep, and deviations in the photon ring would constrain the exterior corrections, not directly reveal the interior. But an exterior correction is a clue about what interior theory produces it. The connection between interior structure and exterior geometry is not arbitrary. It is set by the equations of whatever theory governs the interior. A measured deviation would narrow the field of viable interior theories. What we currently have, BUM M87 and Sagittarius A star, is confirmation that the exterior geometry is consistent with Kerr to the precision of current measurements. That confirmation is not trivial. The objects at the centers of these galaxies could, in principle, have been exotic compact objects, quark stars, boson stars, gravastars that mimic black holes in their gravitational influence but differ in their near-horizon structure. The photon ring images constrain how closely those objects must mimic Kerr if they are to be consistent with observation. The constraints are tight enough to rule out many exotic alternatives and leave a much smaller space of viable theories. The space is not empty. Within it, the fuzzball, the Planck star, the holographic encoding, and the classical singularity all remain formally consistent with what the images show. Distinguishing between them will require either the subring measurements or a detection of quantum corrections to Hawking radiation from an evaporating primordial black hole, or some other observation that probes a regime the current instruments cannot reach. The photon ring is the closest we can come to seeing the event horizon directly. It is not the horizon. It does not show us what is inside. It shows us the region just outside the shell of unstable photon orbits that surrounds the horizon, lit by the radiation of infalling gas, shaped by the curvature that the mass within creates. It is a signature, not a window. And what it most precisely tells us is the same thing the entire series of acts has been building toward: that we can measure the exterior of a black hole with extraordinary precision, that general relativity describes that exterior correctly to within current measurement uncertainties, and that the interior, the singularity or whatever replaces it, the other side or whatever exists there, the fate of the information, or however it is preserved, remains, for now, beyond the edge of what any observation can reach. Whether it will always remain beyond that edge, or whether some future instrument or some future theoretical insight will find a way through, is the question this series has been circling from the beginning. Not what is on the other side of a black hole. That question has 4 serious answers, none confirmed. But whether the other side is, in any physical sense, accessible to us from here. Whether the information encoded on the horizon can be decoded by someone outside. Whether the geometry connecting the interior to the external radiation through entanglement wormhole structure constitutes a kind of accessibility, even if not a traversable one. Whether the photon ring, measured with sufficient precision, will carry in its substructure the first trace of an answer. And whether that answer, when it comes, will resolve the paradox, or reveal that the paradox was pointing at something deeper than either quantum mechanics or general relativity, alone or together, currently has the language to describe. Thank you for staying this long. Not everyone does. And the ones who do, I think you already know why you're here. Whatever question is still turning in your mind right now, let it. The best ideas don't resolve before sleep. They just get quieter. Rest well. I'll see you next time.